High above the clouds of Uranus, sunlight fades into an endless turquoise twilight. It is a planet that rolls on its side, spinning like a wounded marble, wrapped in winds faster than sound. For centuries, it has waited, distant, pale, and forgotten, on the edge of our solar system. Yet, beneath its serene beauty lies a truth that humbles even the most advanced civilizations. We can see Uranus with our telescopes, we can calculate its storms and measure its rings. But there's one thing humanity may never do: set foot there. Why can't we ever reach Uranus? What barrier lies beyond technology, beyond physics, beyond will? Like and subscribe as we embark on a journey to the frozen giant at the edge of possibility. Let's begin. From a distance, Uranus glows like an ocean suspended in darkness, but its calm appearance hides a world colder, stranger, and more hostile than any place humans have ever imagined. To the naked eye, Uranus looks peaceful, a soft cerulean marble drifting silently through the black sea of space. But that soothing glow is an illusion. Beneath its calm surface lie forces that defy comprehension. Uranus is not a solid world, but a giant sphere of gas, ice, and pressure, a planet that exists on the edge between the familiar and the alien. It is a place where water becomes metal, where air turns to liquid, and where sunlight dies long before it reaches the ground that doesn't exist. Discovered in 1781 by the astronomer William Herschel, Uranus was the first planet found with a telescope, a discovery that expanded humanity's understanding of the solar system overnight. At first, scientists thought it was a star or perhaps a distant comet. But when its slow, deliberate orbit became clear, so too did the realization that the solar system was far larger than anyone had ever dreamed. Herschel's new world was twice as far from the Sun as Saturn, and nearly invisible to the unaided eye. It marked the beginning of a new kind of astronomy, one that relied not on curiosity alone, but on the power of our instruments to reveal what human senses could not. And yet, more than 2 centuries later, Uranus remains one of the least understood planets in our neighborhood. We have maps of Mars detailed down to the size of a house, and images of Jupiter's storms swirling in motion. But Uranus? We've seen it up close only once, for a few fleeting hours. When Voyager 2 flew past in 1986, it captured a handful of pale, ghostly images. No mountains, no canyons, no drama. Just a smooth, almost featureless sphere adrift in deep space. It was beautiful, but unnervingly empty, as if the planet were hiding something. That blank blue surface tells a story of unimaginable cold. Uranus is the coldest planet in the solar system, reaching temperatures as low as negative 224 degrees Celsius. The Sun there is nothing more than a bright star, its warmth so faint that the upper atmosphere never stirs enough to reveal what truly lies beneath. And yet, despite that frigid calm, the winds on Uranus howl faster than any hurricane on Earth, jet streams that move faster than sound. Inside that quiet blue sphere rages chaos that human eyes have never seen. To the ancient astronomers, the outer planets were gods. Jupiter, the king. Saturn, the reaper of time. Neptune, the sea's abyss. But Uranus, named for the sky itself, is something else entirely. It is the ghost of the solar system, drifting beyond the reach of warmth or comfort, a frozen memory of creation itself. Everything about it seems designed to remind us of distance, of silence, of how small we are in the endless night. Perhaps that's why Uranus feels so otherworldly. It's not merely distant in space, it's distant in kind, too faint for the naked eye, too cold for light to linger, too strange for our machines to survive for long. A pale beacon in the dark, whispering a truth we are still learning to hear. Not every world wants to be reached. Some are meant only to be witnessed, forever glowing, forever alone, the blue ghost of the solar system. Astronomers once believed Uranus defied the very rules of planetary formation, a world tilted 98 degrees on its side, as if some cosmic hand had struck it billions of years ago. In the quiet mathematics of the cosmos, planets are supposed to obey a certain order. They form from swirling disks of gas and dust, aligning neatly with their star's rotation, their poles pointing roughly in the same direction. But Uranus breaks every rule. It rolls through space like a marble knocked off its axis, its equator pointing toward the sun, while its poles take turns basking in decades of light and shadow. It shouldn't move this way, and yet it does, calmly, confidently, as though defiance itself were written into its nature. Scientists call it an axial tilt, but that term hardly captures the strangeness of what happened here. Somewhere in the early chaos of the solar system, when planets were still forming and collisions were common, Uranus was struck by something enormous, perhaps a world the size of Earth, perhaps larger. The impact was so powerful it not only tipped Uranus onto its side, but may have shattered its internal structure, scattering heat, light, and symmetry like a broken mirror. From that moment on, Uranus became an outlier, a planet born of violence, moving through eternity in quiet disarray. This tilt changes everything. On Earth, the sun rises and sets every day. On Uranus, a single sunrise can last 40 years. When its north pole faces the sun, half the planet is plunged into decades of daylight while the other half disappears into a winter that seems endless. Then, as Uranus continues its long 84-year orbit around the sun, the situation reverses. Seasons there aren't measured in months, they are epochs. If you were standing on one of Uranus's icy moons, you would watch the sun trace strange circles across the sky, dipping lower each decade until it vanishes completely for half a human lifetime. Even the planet's magnetic field refuses to behave. Instead of being aligned with its rotational axis, like Earth's, Uranus's magnetic field is wildly off-center, tilted by nearly 60 degrees and offset from the core by thousands of kilometers. The result is a magnetic environment that twists and flips as the planet spins, creating a constantly shifting field of radiation. If Earth's magnetic field were a compass, Uranus's would be a spinning kaleidoscope, unpredictable and surreal. The mystery of Uranus's tilt isn't just an astronomical curiosity, it's a cosmic wound frozen in motion. That ancient collision might explain why Uranus emits almost no internal heat. When the impact occurred, its molten core could have been displaced or sealed beneath layers of ice, trapping its energy forever. In the aftermath, the planet cooled, dimmed, and fell silent. It became the first ice giant, a hybrid world made of rock, water, methane, and memory. When scientists model the early solar system, they often struggle to recreate Uranus's orbit and orientation. It simply doesn't fit. Every simulation ends with a planet too stable, too aligned, too ordinary. It's as though Uranus is the solar system's own paradox, a reminder that even in the precise dance of gravity and motion, there is room for chaos. Perhaps that's why Uranus feels so haunting. It exists against the odds, a celestial survivor of unimaginable violence, still spinning sideways after 4 billion years. A planet that shouldn't exist, and yet does. Proof that even the universe, in all its order and symmetry, sometimes makes beautiful mistakes. Unlike any other planet, Uranus spins horizontally, its poles facing the sun while its equator lies in shadow. This rotation creates seasons that last 42 years each, years of light and decades of night. Imagine standing on one of Uranus's icy moons, Miranda, perhaps, its fractured canyons towering higher than Mount Everest. Above you, the planet fills half the sky, a turquoise giant lying on its side, rotating like a wheel instead of a top. Its rings rise vertically from pole to pole, slicing through space like a tilted halo. One hemisphere glows under eternal sunlight, while the other sleeps in deep, endless night. And in between, a twilight zone circles the planet forever. A band of perpetual dusk where the sun never rises or sets. This bizarre orientation changes everything about how Uranus experiences time. On Earth, Our 23-degree tilt gives us familiar cycles of spring and winter, of days and nights in balance. But on Uranus, the tilt is almost 5 times greater. When its north pole faces the sun, it stays in daylight for more than 4 decades, while the south pole freezes in a night that lasts just as long. Then, halfway through its 84-year orbit, the planet turns over and the roles reverse. For the inhabitants of an imaginary Uranian colony, summer would mean half a lifetime of sunlight, and winter a generation of darkness. Even more astonishing is what this sideways spin does to the planet's atmosphere. As Uranus rolls around the sun, its layers of hydrogen, helium, and methane respond in strange ways. Winds change direction. Jet streams fold in on themselves. Storms the size of continents appear and vanish without warning. The planet's seasons unfold not in days or months, but in slow-motion surges, currents of gas shifting over decades, creating weather patterns no computer can yet predict. Voyager 2's brief flyby in 1986 caught Uranus at its southern solstice, when the South Pole faced directly toward the Sun. The spacecraft's cameras saw an eerily uniform disk. No clouds, no storms, no bands like Jupiter or Saturn. Just a pale blue circle, motionless and calm. But years later, as Uranus began to tip into its next season, telescopes on Earth detected something unexpected. Activity. Bright spots appeared. Clouds rose from the depths. The planet, dormant for decades, had begun to awaken. Scientists now believe Uranus's extreme tilt may drive an internal rhythm, an atmospheric heartbeat that pulses over centuries. When one pole basks in sunlight, energy slowly stirs deep within the planet. When it turns away, the trapped warmth ignites turbulence, releasing that energy in vast, slow-moving tempests. Each season becomes a kind of planetary breath, inhale, exhale, spanning nearly a human lifetime. To us, the sideways world of Uranus feels alien, but in truth, it mirrors a deeper truth about the universe. Even the laws of motion can twist themselves into something strange and beautiful. Here, day and night are not moments but eras. Time itself feels stretched, distorted by geometry and distance. And as the planet rolls endlessly through space, its tilted rings catching faint sunlight, Uranus becomes a reminder that there is no single way to turn, no single rhythm to follow. In the quiet dark beyond Saturn, a sideways world spins on, serene, defiant, and utterly unique. Scientists believe Uranus was once upright, until a world the size of Earth slammed into it, tilting its axis and rewriting its destiny forever. 4 billion years ago, the early solar system was chaos incarnate. Planets were still forming, their orbits unstable, their paths crossing in violent encounters that shaped the architecture of everything we know today. In that cosmic melee, worlds collided like celestial billiard balls, leaving behind scars that still mark their surfaces and orbits. But few collisions were as catastrophic or as transformative as the one that befell Uranus. The evidence is written into its very being. Uranus's 98-degree tilt is too extreme to have happened gradually, and its internal structure hints at trauma buried deep within. Computer models suggest that an object roughly the size of Earth, or perhaps even larger, slammed into Uranus at an oblique angle. The impact was so violent that it may have knocked the young planet onto its side, vaporized part of its outer atmosphere, and reshaped its magnetic field forever. This was not a simple glancing blow. It was an event powerful enough to melt rock, shatter cores, and tilt destiny itself. For a moment, the planet must have glowed with unimaginable heat, its atmosphere boiling, its oceans of ice and gas torn apart and reassembled in seconds. Then, slowly, gravity pulled it all back together into the calm, tilted giant we see today. A frozen world born from fire. That ancient collision may also explain another of Uranus's mysteries, its eerie lack of internal heat. Unlike Neptune, which radiates far more energy than it receives from the Sun, Uranus is strangely cold and inert. Scientists think the impact could have disrupted its interior so completely that heat from the core became trapped under dense layers of ice, unable to escape. The result is a planet that glows faintly in the infrared, but emits barely any warmth, a frozen heart beneath a silent sky. The collision theory also helps explain Uranus's irregular magnetosphere. Its magnetic field isn't centered or aligned with its spin. Instead, it's tilted and displaced, as if the planet's magnetic poles were torn from their roots. This offset creates a bizarre, twisting field that corkscrews through space as Uranus rolls along its orbit. Each rotation causes its magnetic poles to sweep in wide circles, producing auroras that flicker unpredictably across its poles, ghostly lights born from the memory of an ancient impact. And perhaps most hauntingly, that cosmic catastrophe may have spawned Uranus's moons. The debris ejected from the collision likely coalesced into a delicate family of satellites: Ariel, Umbriel, Titania, Oberon, and Miranda, each orbiting in strange harmony with the planet's tilted equator. They, too, are children of the impact, fragments of a shattered world forever bound to their wounded parent. In the stillness of space, Uranus drifts on, serene, distant, and forever sideways. But hidden within that quiet blue sphere is the record of unimaginable violence. Every rotation, every tilt, every glimmer of auroral light is a whisper of what once happened there, a moment when worlds collided and a planet's fate was rewritten. It's easy to look at Uranus and see calmness. But beneath that calm lies history, measured in cataclysms. The collision didn't just tilt a planet, it transformed it into something entirely new. A world shaped by destruction, forever carrying the memory of the day the heavens themselves changed course. Deep beneath its pale clouds lies a shattered core, ice, rock, and metallic water crushed by millions of atmospheres of pressure, locked away since the birth of the solar system. If you could somehow descend through Uranus's turquoise atmosphere, you would find no solid ground waiting below, only endless layers of mystery. The journey downward would begin gently, through thin clouds of hydrogen and helium, tinted blue by traces of methane gas. But with each passing kilometre, the air would thicken until it became a liquid, then something stranger still, an exotic, shimmering state of matter neither solid nor gas, a soup of elements caught between worlds. At depths thousands of kilometres below the clouds, pressure rises to unimaginable levels, millions of times greater than on Earth's surface. Molecules are squeezed so tightly together that chemistry itself begins to change. Water, ammonia, and methane stop behaving like the substances we know. They fuse into strange electrically conductive fluids that scientists call supersonic ices. Here, oxygen atoms form rigid lattices, while hydrogen ions drift freely through them, creating something that behaves almost like metal. It is ice that conducts electricity, ice that glows, ice that could generate a magnetic field. This is the fractured heart of Uranus, a realm of crushing weight and alien physics. Somewhere deep within, this metallic ice transitions into a core of rock and dense minerals, perhaps fractured and displaced by the ancient collision that knocked the planet onto its side. Unlike the molten iron core of Earth, Uranus's interior seems scattered, its layers blurred and uneven. Computer models suggest that chunks of its core may even float within its fluid mantle, fragments adrift in seas of compressed water and ammonia. The result is a planet that defies simple structure. On Earth, we can map clear boundaries between crust, mantle, and core. On Uranus, those divisions dissolve. It is as though the planet's insides have been stirred by some cosmic hand, its materials mixed, its layers twisted, its identity rewritten. This chaotic interior might explain its strange magnetic field, offset and tilted like a compass gone mad. Rather than arising from a single central core, Uranus's magnetism may come from moving currents in these metallic oceans, looping and folding through the fractured depths. And yet, despite the turmoil within, the outer world remains eerily still. Uranus radiates almost no heat to space, its internal energy sealed away, trapped by the same dense layers that shattered long ago. The planet's heart beats quietly, if at all, its warmth buried beneath a shell of eternal frost. Scientists believe that understanding this interior could reveal the blueprint for countless other ice giants across the galaxy. Worlds like Uranus and Neptune are among the most common types of planets we've found orbiting distant stars. To study Uranus is to study a cosmic archetype, a model for what billions of other worlds might be. But to reach that heart, to feel its metallic seas and measure its hidden currents, we would need to send a probe deep below the crushing pressure. No machine we've built could yet survive that descent. And so, for now, the heart of Uranus remains untouched, a broken relic of creation, sealed beneath layers of cold and time. It is there, in that buried ocean of metal and ice, that the planet keeps its oldest secret. The memory of the moment it was made. A fractured heart, still beating in the silence of eternity. Uranus is silent, yet its winds scream at nearly 900 kilometers per hour, jet streams that could shred steel, unseen storms roaring beneath a placid blue veil. From Earth, Uranus appears calm and unchanging. Its pale blue surface shows no stripes or swirls like Jupiter's, no vast hexagonal storms like Saturn's. But that illusion of stillness is one of the greatest tricks in the solar system. Beneath that calm facade lies an atmosphere in motion, furious, relentless, and unlike anything on Earth. The winds on Uranus race around the planet faster than the speed of sound, invisible to the naked eye but powerful enough to move entire layers of its atmosphere in chaotic harmony. These winds blow eastward and westward in alternating bands, forming jet streams that circle the planet's poles and equator. At their peak, they reach velocities of over 900 kilometers per hour, nearly the speed of a bullet. Yet from above, all we see is serenity. A smooth, featureless globe the color of tranquil seas. That's because Uranus's atmosphere is composed mostly of hydrogen and helium, with just enough methane to scatter sunlight and mask the violence below. Voyager 2 was the first to glimpse hints of this hidden turmoil during its brief flyby in 1986. While its cameras revealed a bland, pale world, subtle temperature measurements told another story. Beneath that motionless surface, heat gradients hinted at movement, at vast, invisible rivers of gas flowing with unimaginable speed. Later observations from Earth-based telescopes, using infrared imaging, finally revealed faint streaks and bands of motion, confirming what Voyager had only suggested. Uranus is a world of storms cloaked in silence. The cause of these supersonic winds remains one of the planet's great mysteries. Normally, such immense velocities would require internal heat to drive convection, rising and sinking currents of gas, like the systems that fuel Jupiter's Great Red Spot. But Uranus emits almost no internal energy. Its core is cold, its heat long lost. So where does the energy for such furious motion come from? Some scientists suspect that the winds are powered not from within, but from without. At Uranus's immense distance, the sun still exerts a faint but steady influence, heating the planet unevenly as its tilted axis rolls through its 84-year orbit. For decades, one pole basks in continuous sunlight while the other freezes in darkness. This slow, colossal imbalance may create atmospheric tides, gradual but relentless shifts that build momentum over decades, eventually igniting storms that can last for centuries. Others propose that Uranus's unusual rotation and magnetic field twist its atmosphere into motion. As the planet rolls through space, its off-center magnetosphere may drag against charged particles in the solar wind, transferring energy into its upper layers and driving colossal air currents across the globe. Whatever the source, the winds of Uranus are among the fastest in the solar system, stronger than any hurricane, more enduring than any jet stream on Earth. If you could float above the clouds, the sound would never reach your ears, the air is too thin to carry it. But the motion would be immense, the pressure endless, a planet's atmosphere endlessly in flight, never resting, never slowing. From a distance, Uranus looks peaceful, like the surface of a still lake under twilight. But up close, that lake becomes a tempest of frozen air, moving faster than sound, erasing every boundary between calm and chaos. Beneath its veil of blue lies the quiet roar of eternity, the whisper of a world that never truly stands still. Unlike Jupiter or Neptune, Uranus barely radiates any warmth. It should be glowing with internal energy, but it isn't. It's as if the planet's heart went cold long ago. Every planet keeps a kind of memory within it, a leftover warmth from the day it was born. When worlds form, the energy of collisions, compression, and radioactive decay traps heat inside them, slowly leaking into space over billions of years. Jupiter and Saturn still glow faintly from this internal fire, radiating more energy than they receive from the Sun. Even Neptune, Uranus's near twin, burns with a hidden furnace deep within, but Uranus does not. It is the quiet one, the frozen one, the planet that forgot to keep its own warmth. When Voyager 2 flew past Uranus in 1986, scientists were stunned by the readings. The spacecraft detected almost no internal heat source, less than 1/10 of what they expected. The planet was radiating only as much energy as it received from sunlight, despite being nearly 3 billion kilometers away. By comparison, Neptune, nearly as distant, shines with more than twice that amount. It was as though Uranus's internal fire had gone out. Why? No one is sure, but the leading theory points to the same event that tilted Uranus on its side, a colossal impact during the solar system's violent youth. When the proto-Uranus collided with another massive body, the energy of the impact may have rearranged its core, scattering and sealing layers of material that once allowed heat to escape. Like a fractured thermos, the planet could have trapped its warmth deep inside, hidden behind barriers of supersonic ice. Over time, that inner energy might have stagnated, cooling so efficiently that the world effectively froze from the inside out. Other scientists suggest an even stranger idea, that Uranus's internal heat is still there, but locked away, unable to reach the surface. If the planet's interior is composed of uneven layers of different ices and gases, those materials could act as insulators, blocking convection currents that normally carry heat upward. Beneath its serene blue clouds, Uranus might still hold a smouldering core, buried under oceans of metallic water and methane ice. A heartbeat that no longer reaches the surface. Yet the lack of heat only deepens Uranus's mystery. The frigid calm of its atmosphere, the stillness of its surface, even its gentle hue, each one may be a product of this quiet energy loss. Without internal warmth to stir convection, Uranus's weather becomes slow and ghost-like. Storms appear not as roaring tempests but as faint smudges of motion in a sea of calm. The planet's very personality, its silence, its distance, its indifference, may be the echo of a frozen soul. Some astronomers call Uranus the sleeping giant, a world that once burned bright but has drifted into eternal slumber. And yet, even sleep can hide strange dreams. Subtle variations in its infrared glow suggest that beneath its icy stillness, Uranus may still hold pockets of warmth, remnants of a world that was once alive with motion. Perhaps one day, a future probe will descend through those clouds and feel it, a faint radiance, a hidden ember beneath the frost. Until then, Uranus remains the loneliest of the giants, a planet whose silence speaks of something ancient and forgotten. A reminder that even worlds can lose their light, and that sometimes the coldest places are the ones that once burned brightest. For decades, scientists have searched for the reason why Uranus emits so little heat. Some believe its catastrophic collisions scattered its warmth into space forever. When Voyager 2 drifted past Uranus, the data it sent home confounded every model astronomers had built. According to physics, the planet should have been glowing faintly with internal warmth, releasing the leftover energy from its violent birth. But it wasn't. The readings showed something impossible. A world colder than it should be, a planet that had somehow lost nearly all of its heat to the void. The deeper scientists looked, the stranger the mystery became. Neptune, almost the same size and composition, radiates 2.6 times the energy it receives from the Sun. By comparison, Uranus barely manages to give off as much as it takes in. The two are planetary twins, formed in the same region, made of the same materials, yet one burns with hidden vitality while the other drifts in quiet frost. Somewhere in their shared history, something diverged. Something happened to Uranus that extinguished its inner fire. The leading theory is still the ancient collision, the same cataclysm that tilted Uranus onto its side. That massive impact may have done more than just rotate the planet. It could have ripped open its atmosphere, venting primordial heat into space in an instant. Imagine a world glowing with molten light, its gases ripped apart by the shockwave of a planetary impact. Over hours or days, its warmth would have poured into the blackness, cooling too quickly to ever recover. The result? A wounded world, sealed in its own silence, forever colder than its peers. But there's another possibility, one more subtle and perhaps more haunting. What if Uranus's heat is still there, hidden beneath layers so thick that it can no longer escape? Deep within its subaerionic oceans, the flow of heat may be trapped by uneven layers of ice and gas that resist convection. Instead of rising upward, that warmth circulates endlessly within, locked in an eternal loop. But beneath the surface, a ghostly current might still pulse, slow, quiet, undetectable. Some astrophysicists also speculate that Uranus's missing energy might be linked to its strange magnetic field. Because the field is so off-center and tilted, it may interact with the planet's interior in ways we don't yet understand, possibly diverting or dampening the transfer of heat. If so, Uranus's very geometry, its sideways rotation and lopsided magnetism, might be the key to its coldness. A self-inflicted paradox of motion and magnetism. Whatever the cause, Uranus's missing energy remains one of the greatest unsolved mysteries of our solar system. It challenges our understanding of how planets evolve, how they age, and how fragile balance can be on a cosmic scale. To this day, no spacecraft has returned to Uranus to take a closer look. The data we have is decades old, a handful of glimpses from a single passing probe. Somewhere beneath those layers of ice-blue clouds, the planet guards its secret, whether it's the silence of a frozen heart or the quiet hum of heat still trapped within. Perhaps Uranus's missing energy isn't lost at all. Perhaps it's a story still unfolding, a reminder that even when a world seems still, the forces that shaped it may still be whispering in the dark, waiting for us to listen closely enough to hear them. Despite being one of the coldest places in the solar system, Uranus's atmosphere swirls with methane, an element that should trap heat but instead reflects it away. It's one of the great cosmic ironies, a planet wrapped in what should be a blanket, but instead wears a mirror. On Earth, methane is a greenhouse gas, a molecule that traps warmth and keeps our atmosphere stable. Yet on Uranus, this same substance does the opposite. It sends sunlight back into space, scattering blue wavelengths and leaving the planet colder, dimmer, and eerily still. It is a world insulated not by warmth but by reflection, a paradox written in pale cyan. At first glance, one might imagine that a planet coated in methane would shimmer with heat. But the truth lies in the nature of light itself. Methane absorbs red light and reflects blue, giving Uranus its tranquil hue. At 20 times Earth's distance from the Sun, the sunlight that falls on Uranus is 400 times weaker. What little energy the planet receives is bounced back into space before it can warm the atmosphere. The result is a paradoxical combination of ingredients: an insulating gas that cannot insulate, and a distant sun too faint to help. This strange chemistry helps explain Uranus's uncanny calm. The upper layers of its atmosphere are so cold and dense that motion slows to a crawl. The planet's storms, vast and slow-moving, are muted, their thunder hidden beneath methane clouds. Even lightning, which Voyager 2 detected faintly in 1986, seems to move in slow motion, trapped in a frozen ballet of static electricity. Deeper below, the paradox continues. The heat that Uranus should be radiating from its interior, leftover warmth from its formation billions of years ago, is barely detectable. The planet emits almost no infrared energy at all. It's as though Uranus has turned off its internal furnace. Some scientists believe that, long ago, an enormous impact knocked the planet on its side and vented its primordial heat into space. Others think that its interior structure traps warmth in strange, unmoving layers, heat buried so deep it can never escape. Either way, the result is haunting. A world that should be warmer, but isn't. A planet made of gases that should breathe energy, but instead exhale silence. Uranus stands as proof that the laws of nature don't always behave intuitively, that what sustains one world can freeze another. In this contradiction lies something quietly poetic. Uranus is not just a cold planet, it's a mirror of what happens when distance and chemistry conspire to still the heartbeat of a world. It reflects light the way solitude reflects thought, beautifully, but at a cost. From afar, we see that gentle turquoise glow and think of peace. But that serenity is built on tension, a perfect balance between what absorbs and what denies, between heat and emptiness. Uranus, the frozen paradox, reminds us that in the cosmos, even opposites can coexist in harmony. Here, in its silent layers of reflective blue, warmth and cold meet and cancel each other out. The result is not chaos, but calm, a world where contradiction becomes equilibrium, and where stillness itself becomes the final expression of balance. When Voyager 2 flew past Uranus in 1986, it discovered a delicate set of black rings so dark they absorbed nearly all sunlight, shadows circling a ghost. Until that moment, few believed Uranus had rings at all. Saturn's brilliant halos had long stolen the spotlight, their golden arcs so bright they could be seen through small telescopes on Earth. Jupiter and Neptune were known to have faint ring systems too, thin and dusty, but Uranus? It seemed bare, silent, smooth. Only when Voyager's cameras adjusted their exposure to near darkness did something remarkable appear. A system of 13 slender rings, dark as soot, nearly invisible. Not circles of light, but circles of shadow. These rings are not like Saturn's, shimmering plains of ice stretching thousands of kilometers wide. Uranus's are sparse, sharp-edged, and almost black. They reflect less than 2% of the sunlight that strikes them. If Saturn's rings are music, Uranus's are the quiet notes between. Each ring is made of icy fragments coated with radiation-darkened dust, the remnants of shattered moons or captured debris, long since sculpted by gravity. Their darkness is what makes them so haunting. In most of the solar system, light is a storyteller. It reveals, it defines. But around Uranus, light vanishes. The rings seem carved from absence itself, thin ribbons of nothingness orbiting a planet already wrapped in mystery. If you look toward them from space, you might not see them at all. Only when they catch a sliver of sunlight do they reveal their presence, brief crescents glinting before fading again into the void. Scientists believe these rings are relatively young, perhaps no more than a few 100 million years old, a blink in cosmic time. They could be the remains of moons torn apart by Uranus's gravity, pulverized into dust and stone. Or perhaps they formed from collisions between icy bodies that strayed too close, each impact leaving behind a trail of dark debris. Over time, those fragments gathered into thin bands, held in place by tiny shepherd moons that orbit nearby, keeping the edges clean and sharp. It's strange to think of something so delicate existing in such a violent place. The rings are fragile, thin as paper, wide as continents, yet they endure, orbit after orbit, circling a planet that barely glows. When Voyager 2 looked back one last time before leaving, sunlight caught the rings at an angle, turning them into glowing arcs suspended against darkness. For a moment, Uranus looked almost angelic, not the silent giant we knew, but a sleeping world wearing a faint crown of shadow. Even today, those rings remain nearly invisible to ground-based telescopes. Only with the Hubble Space Telescope, and now the James Webb Space Telescope, have we been able to glimpse them again. Faint, fragile, and eternal. They remind us that beauty doesn't always announce itself. Sometimes it hides in plain sight, waiting for the right light to reveal it. The rings of Uranus are proof that even in the outer dark, elegance persists. They are the whisper of a world that refuses to fade, not bright enough to be seen easily, not loud enough to be heard, but still there, circling endlessly. Silent shadows keeping time with a planet that has mastered the art of stillness. Uranus has 27 moons, each scarred, frozen and silent. Some may hide underground oceans. Others are relics of ancient worlds torn apart by gravity. They orbit like fragments of a forgotten story, small, pale bodies circling a planet that barely shines. The moons of Uranus are not grand like Jupiter's Galilean giants, or as dazzling as Saturn's icy pearls. Instead, they are worlds of shadows and frost, their surfaces fractured by time, their names borrowed from Shakespearean and Alexander Pope characters: Miranda, Ariel, Umbriel, Titania, Oberon. It's a fitting choice, for they are as tragic and poetic as the plays that gave them their names. Each moon is unique, yet all share the same haunting beauty. Miranda, the innermost of the large moons, is one of the strangest objects in the solar system. Its surface looks shattered and rebuilt, cliffs towering 20 kilometers high, canyons deeper than Earth's Grand Canyon, and scars that suggest the moon was once broken apart and reassembled. It may have been torn to pieces by Uranus's gravity, then slowly drawn back together, frozen into a mosaic of old wounds. It is a world that has died and been reborn, still carrying the marks of its violent resurrection. Farther out, Ariel gleams slightly brighter, smoother, younger, as if something beneath its surface still stirs. Scientists suspect that internal heat, though faint, may once have melted pockets of water below the crust. Perhaps even now, beneath the frozen plains, hidden oceans linger, seas locked beneath hundreds of kilometers of ice, waiting in the dark. Umbriel, by contrast, is dim and ancient. It reflects almost no light, a moon of pitch and shadow. Its surface is cratered and still, untouched for eons. Titania and Oberon, the two largest moons, show similar signs of age: icy mountains, rift valleys, and impact scars that have remained unchanged for billions of years. These moons are cosmic time capsules, keeping the memory of a solar system still young and restless. Unlike the moons of Jupiter or Saturn, those of Uranus orbit in the planet's tilted plane. When one pole of Uranus faces the Sun, the same happens to its moons, half of their orbits bathed in light for decades, the other half swallowed by darkness. Imagine standing on Titania and watching the Sun skim the horizon for 40 years before disappearing for another 40. Day and night are replaced by eras of light and shadow. There are also the tiny inner moons, irregular, potato-shaped bodies no wider than a city, tumbling chaotically through the planet's rings. Some of these are shepherd moons, maintaining the sharp edges of the rings through their gravity. Others drift like debris, remnants of ancient collisions, their fates uncertain. Together, these moons form a silent ballet around Uranus, an intricate dance choreographed by gravity and time. They do not shine brightly, nor do they call attention to themselves. Yet in their quiet orbits, they embody something profound: endurance. Worlds that have endured collisions, darkness, and unimaginable cold, still moving faithfully around their parent planet, century after century. If we could listen to Uranus's moons, perhaps they would not speak in words or sound, but in patience. Their frozen landscapes whisper stories of survival, of worlds broken and remade, of seas turned to stone, of light that never quite reaches them. In the darkness beyond Saturn, these moons keep their lonely vigil. They circle a sleeping planet, their icy faces turned outward toward the stars, as if still waiting for someone to return and remember their names. Even Uranus's magnetic field defies logic, angled, off-center, and wobbling wildly, as if the planet's invisible heart beats to a different rhythm than its spin. In most planets, magnetism follows order. Earth's magnetic poles roughly align with its axis of rotation, creating the graceful curtains of the aurora borealis. Jupiter's vast magnetic field extends millions of kilometers outward, steady and predictable. But Uranus is different. Its field is tilted nearly 60 degrees away from its spin axis, and its magnetic center doesn't even pass through the planet's core. It's offset by thousands of kilometers. Imagine a bar magnet placed not at the planet's center, but near one side, spinning unevenly like a top that's lost balance. The result is chaos. As Uranus rotates, its magnetosphere, the invisible bubble of magnetic force surrounding it, doesn't simply spin. It tumbles, sways, and warps. Every 17 hours, the field twists on itself, causing regions of magnetic energy to flare and collapse unpredictably. It's a magnetic field in motion, alive with turbulence, reshaping constantly as if it cannot make up its mind. When Voyager 2 flew past in 1986, scientists expected to find something similar to the steady magnetic fields of Jupiter or Saturn. Instead, they discovered this tilted, lopsided enigma, a field unlike any other in the solar system. It was as though Uranus had built its magnetism not from symmetry, but from defiance. Its northern and southern magnetic poles don't line up with its geographic poles, and the field's strength varies wildly depending on where you measure it. The cause of this magnetic misalignment remains one of Uranus's greatest mysteries. Some researchers believe it's due to the planet's internal structure. Perhaps the magnetic field isn't generated in a molten metal core, like Earth's, but within an icy shell of water, ammonia, and methane that behaves like a conductive fluid under immense pressure. If so, Uranus's magnetism is born not in fire, but in frozen motion, a churning sea of slush and electricity far below its clouds. Because of this bizarre geometry, Uranus's auroras, the glowing curtains of light that dance at its poles, don't stay in place. They wander. Instead of circling the poles neatly, as they do on Earth, Uranus's auroras drift across the planet's surface unpredictably, flickering and fading in strange tilted arcs. Seen from space, it's as if the planet's glow itself is searching for balance, tracing shapes that never repeat. This instability creates a magnetosphere unlike any other. It stretches far into space, twisting like a ribbon in the solar wind. At times, the field may even flip direction entirely, briefly exposing the planet's atmosphere to radiation from the sun before snapping shut again. Uranus's magnetic environment is, in a sense, alive, breathing in solar energy, exhaling charged particles into the dark. Yet, even in this chaos, there is elegance. Tilted magnetosphere is a reminder that the universe rarely follows the rules we expect. Symmetry, balance, and order. These are human preferences, not cosmic laws. Uranus seems to dance to its own rhythm, its magnetic heart beating out of sync with its spin, its field a pulse that refuses to conform. To some, it feels almost poetic. A planet that rotates on its side, wrapped in a magnetic field that tumbles and twists just as wildly, both body and spirit tilted forever. Uranus embodies the beauty of imperfection, the artistry of asymmetry. Its magnetism is not a flaw but a fingerprint, the unique, unrepeatable signature of a world that refuses to stand upright yet still shines in the dark. Every orbit, Uranus doesn't just spin, it rolls, dragging its rings and moons through the void like a marble tumbling in slow motion around the sun. Most planets turn like tops, upright and balanced, their poles steady and sure. But Uranus turns like a sleeper rolling in a dream, tilted on its side, its equator nearly vertical to the plane of the solar system. From a distance, it appears to drift lazily through space, its poles alternately facing the sun as it moves along its 84-year orbit. For more than 4 decades, one hemisphere basks in sunlight while the other lies in endless night. When Uranus finally reaches the opposite side of its orbit, it rolls again. The day becomes night, and the night, day. This strange orientation changes everything about the planet's seasons, weather, and light. Unlike Earth's gentle cycles, Uranus's seasons are extremes of stillness and transformation. Imagine a world where summer means 40 years of unbroken daylight, and winter means 40 years of darkness so deep it feels eternal. At the height of its summer, the sun hangs over one pole, fixed in the sky, circling but never setting. Then, as Uranus glides onward, that same region slowly descends into a twilight that will last for the rest of a lifetime. The planet's rings and moons are bound to this same tilted reality. They don't orbit in a flat horizontal plane like Saturn's. Instead, they form a vertical wheel around the planet's sideways axis. Each moon and ring follows that invisible tilt, circling through space like dancers caught in a cosmic tumble. When the sun strikes them just right, the rings flash briefly before vanishing again into darkness, a flicker of light on a rolling world. From a cosmic perspective, Uranus's motion looks almost hypnotic. Picture the entire planet as a glowing blue sphere, slowly rolling through the blackness of space, its rings spinning around it like a halo tipped on edge. The effect is serene yet eerie, a planetary ballet with no audience, performed in silence for billions of years. Scientists believe this peculiar tilt was caused by a colossal impact long ago, perhaps when Uranus was still young and molten. Another planet, possibly Earth-sized, struck it off-center, knocking it onto its side. The impact would have rearranged its core, changed its rotation, and possibly even shattered its moons, which later reformed into the system we see today. The collision's echoes still shape Uranus's existence, its faint heat, its wandering magnetic field, and its strange, sideways spin. In a way, Uranus's sideways motion makes it a cosmic outlier, a planet that refuses to move like the others. While the rest of the solar system whirls in one orderly direction, Uranus glides at an angle, following its own path. It's a reminder that even in the clockwork perfection of the cosmos, individuality endures. The planet rolls onward, steady and unhurried, a turquoise marble tracing an invisible arc around the sun. It doesn't resist its motion, it embraces it, and in that gentle roll lies a quiet wisdom that sometimes the universe does not spin in circles but drifts, gracefully, through eternity. While Mars, Jupiter, and Saturn dominate headlines, Uranus remains largely forgotten. Yet its mysteries may hold the key to understanding the formation of all ice giants. For decades, Uranus has been the quiet one, the overlooked sibling in a family of giants. Mars seduces our imaginations with talk of ancient rivers and the promise of life. Jupiter dazzles with storms larger than Earth itself. Saturn, of course, wears its luminous rings like a crown, commanding every telescope that dares to look up. But Uranus? It drifts in silence, far from the sun, neither bright enough to draw the eye nor active enough to stir excitement. Its pale blue glow is beautiful but subdued, a world that asks for contemplation rather than applause. Perhaps that's why humanity has looked past it for so long. Even in science, visibility often dictates importance. We study what we can see clearly, what moves, what changes. Uranus, however, offers only subtlety. Its features are faint. Its storms are hidden beneath tranquil clouds. Its rings are nearly invisible, and its moons are small, dim, and distant. The planet gives away its secrets reluctantly, whispering rather than shouting. Voyager 2's flyby in 1986 remains our only close encounter. Just 6 hours of data, a handful of images, a stream of readings, a brief visit to a world we've never returned to. In the decades since, our robotic explorers have visited comets, moons, and asteroids, but none have gone back to Uranus. It sits at the edge of exploration's reach, waiting patiently, while our attention drifts elsewhere. Yet within that silence lies untapped wonder. Uranus may hold the answers to some of astronomy's most profound questions: how planets form, how atmospheres evolve, how ice giants shape solar systems. It is the prototype of a class of worlds we now know are common throughout the galaxy. Most of the exoplanets discovered orbiting distant stars are Uranus-like, massive, icy, wrapped in hydrogen and helium. To understand them, we must first understand this quiet one close to home. Scientists are beginning to notice. The James Webb Space Telescope has turned its gaze toward Uranus, capturing faint storms and delicate rings that even Voyager missed. NASA has proposed a dedicated Uranus orbiter and probe, a long overdue mission that would dive into its atmosphere, study its moons up close, and listen for the secrets it has been keeping for billions of years. If approved, it could launch in the 2030s, reaching Uranus in the 2040s, a lifetime away, but worth the wait. Uranus's neglect isn't just about distance, it's about perception. We often chase the spectacular, forgetting that the universe's greatest truths hide in quiet corners. Uranus isn't loud or dramatic. It's introspective, a world defined by stillness, by patience. And maybe that's why we've ignored it. Because in a cosmos filled with fire and fury, Uranus reminds us of the beauty of calm. When future generations finally return to study it up close, they may find that this forgotten world holds the keys to the outer solar system, that beneath its silence lies the blueprint of creation itself. And perhaps then, Uranus will no longer be the planet no one talks about, but the one everyone listens to. Only one spacecraft has ever seen Uranus up close. Voyager 2. For just 6 hours in 1986, it snapped a handful of photos and then continued into darkness. It's almost unthinkable that in all of human history, only one machine has ever been there. One brief encounter, one passing glance, a single hello before an eternal goodbye. Voyager 2 was not built for Uranus alone. It was designed for a grand tour, a once-in-a-lifetime alignment of the outer planets. It visited Jupiter first, then Saturn, using their immense gravity to slingshot itself deeper into the solar system. And then, after nearly a decade of travel through cold and silence, it arrived at a pale blue world no one had ever truly seen. The year was 1986. On Earth, the Cold War rumbled on. The Challenger shuttle tragedy struck just days before the flyby. Humanity looked up at the heavens through grief and wonder, and there, far beyond, a tiny spacecraft made history in silence. Voyager 2 approached Uranus at a distance of 81,500 kilometers, moving faster than any bullet ever fired. For 6 precious hours, its cameras and instruments turned toward the planet, capturing every photon they could before the opportunity vanished forever. The images it sent back astonished scientists, not because they were full of color or detail, but because of how little was visible. Unlike Jupiter's storms or Saturn's bands, Uranus appeared eerily plain, a soft blue sphere with almost no features. No swirling clouds, no great spots, no obvious storms. Just calm, unbroken stillness. Some called it boring, others called it profound. Beneath that blank facade lay mysteries that Voyager's sensors could only hint at. Extreme cold, a tilted magnetic field, faint rings, and moons both scarred and strange. During its brief encounter, Voyager discovered 10 new moons and confirmed the existence of 11 narrow rings. It measured the composition of Uranus's atmosphere, mostly hydrogen, helium, and methane, and mapped its magnetic field, discovering that it was wildly off-center. It even detected lightning deep within the clouds, echoing faintly through the dense atmosphere. For a few fleeting moments, humanity truly saw Uranus, not as a pale dot in a telescope, but as a world. And then, it was gone. After just 6 hours of data collection, Voyager 2 sped onward toward Neptune, leaving Uranus behind forever. The spacecraft didn't slow down. It couldn't. Gravity and momentum pulled it onward, past the last of the giant planets, into the dark beyond. Since that day, no probe, no satellite, no human-made object has returned. Voyager 2 now drifts at the edge of interstellar space, still faintly whispering to Earth across 20 billion kilometers. Its signal takes nearly 18 hours to arrive, a thread of light across eternity. Somewhere on its golden record, among the sounds of wind and ocean and human laughter, lies the proof that we once reached Uranus, however briefly. That 6-hour flyby stands as one of humanity's quietest triumphs, a single blink in time, a lone visitor to a forgotten world. It reminds us how vast our solar system truly is, and how every encounter with another planet, no matter how fleeting, changes the way we see ourselves. Voyager 2 looked at Uranus once. Uranus, unmoving and eternal, has been looking back ever since. Since that flyby, no human probe has returned, no missions are planned in the near future. Uranus waits, silent, untouched, and almost mythic. In the vast map of our solar system, Uranus has become a ghost at the edge of memory, a world visited once, then left to drift in solitude. For nearly 40 years, no spacecraft has ventured close. No camera has captured its horizon, no signal has brushed its atmosphere. The data we have, the few grainy photographs, the faint measurements, all come from Voyager 2's 6-hour encounter in 1986. Everything we know about Uranus fits inside a digital folder smaller than a modern phone app. It's hard to imagine that such a colossal world, 4 times wider than Earth, circled by rings and moons, could remain so neglected. But distance is merciless. At nearly 3 billion kilometers away, Uranus demands patience that technology has yet to match. A probe sent today with the same speed as Voyager would take more than 13 years to arrive. Add the time for development, construction, and alignment, and you're talking about a mission that might not reveal results until the 2040s. In an age of instant information, Uranus moves at a pace that defies our attention spans. It drifts on the outskirts of exploration, too far, too cold, too slow to excite headlines. Space agencies focus on worlds closer to home, where missions can return quick data and dramatic imagery. Mars, with its red dust and robotic rovers, feels reachable. Jupiter and Saturn, with their storms and moons, remain photogenic. But Uranus sits in the quiet between curiosity and neglect. And yet, among scientists, its silence hums like a calling. Uranus represents one of the last unexplored frontiers in our own cosmic neighborhood. Beneath its icy atmosphere could lie the key to understanding not only our solar system's past, but also the architecture of distant star systems. Many of the exoplanets we've discovered are Uranus-like, icy giants orbiting their stars in quiet blue solitude. To understand them, we must first return to the one in our own backyard. Plans have been drawn, Dreams whispered. NASA's proposed Uranus orbiter and probe would be the first mission dedicated to the planet. It would map its magnetic field, study its atmosphere, and explore its moons, tiny worlds that may hide subsurface oceans beneath their frozen crusts. But even if approved, it would take years to build and decades to fly. The future of Uranus exploration is measured not in years, but in generations. And so, for now, Uranus waits. It spins slowly, quietly, completing one revolution every 84 Earth years. Its pale light fades and returns, its seasons shift in silence. No one watches, no one listens, yet it endures. A forgotten world keeping time with eternity. Perhaps that's the lesson it offers us. That discovery doesn't vanish when we turn away. The universe keeps its wonders, waiting patiently for our return. Somewhere out there, Uranus rolls through space, wrapped in clouds of methane and mystery, untouched since 1986. A planet suspended between what we once knew and what we have yet to learn. It is the forgotten frontier, and it waits not with impatience, but with infinite calm. At nearly 3 billion kilometers away, Uranus sits at the edge of reach. Even light takes almost 3 hours to travel from the Sun to its clouds. Distance on this scale is difficult to comprehend. It's not just far, it's transcendent. The kind of distance that makes ordinary measures feel meaningless. On Earth, we think in minutes, miles, and moments, but out here, time itself stretches thin. Light, the fastest thing in the universe, takes almost 9 minutes to reach Earth from the Sun, but nearly 3 hours to reach Uranus. That means the sunlight that touches its clouds left the Sun when the light that now warms your face was still crossing the inner planets. When you look at Uranus, you are not seeing the present, you're seeing the past, delayed by the vastness of space. For a spacecraft, that distance is even more daunting. At the speed of Voyager 2, one of the fastest machines ever built, the trip took almost 9 years. 9 years of silence, of drifting between worlds, of waiting for a signal to cross the void, and that was only a flyby. A true orbital mission, one that slows down enough to stay, would require far more fuel, far more time, and far more patience than we have yet mastered. The emptiness between Earth and Uranus is not like the emptiness between cities or even planets. It is a realm of isolation, so profound that a spacecraft's radio signal weakens to a whisper by the time it arrives. A transmission that begins strong enough to light a bulb on Earth fades to a power smaller than a snowflake's touch. Yet our antennas, vast dishes hundreds of meters wide, can still catch it, turning faint static into meaning. It's a technological miracle, wrapped in cosmic silence. To send a command to a probe near Uranus is to speak into the past. Each instruction takes hours to arrive, and each reply takes hours more to return. You cannot steer in real time. You cannot correct mistakes quickly. You can only hope that what you sent was enough, that the machine understands, that it endures. Out there, autonomy becomes survival. The probe must think for itself, act without guidance, and trust that its creators will one day receive its echoes. The psychological distance is equally immense. When Voyager 2 crossed that gulf, humanity held its breath. There would be no second chance, no follow-up mission. Every photograph, every measurement was precious. Each byte of data was a treasure gathered from a place so distant it defied imagination. And when the probe moved on, a silence followed, the silence of absence, the awareness that we had touched something once and might never touch it again. Yet this impossible distance is not a barrier, it's an invitation. It's what gives Uranus its mystique, its dreamlike pull. To look at it through a telescope, pale and distant, is to feel the weight of perspective. It reminds us how small we are, and how far we've already come. 3 billion kilometers. 3 hours for light, a frontier that humbles even time itself. And yet, within that cold, unreachable span, there is wonder, the kind that reminds us that distance is not the end of discovery, but the reason we seek it. A spacecraft using current technology would take over 15 years to reach Uranus, half a generation before even arriving, and decades more to study it. Space travel to the outer planets is not a voyage measured in miles, but in patience. To reach Uranus is to commit to time itself, to a journey that outlasts projects, politics, and sometimes even people. By the time such a mission arrived, the world that launched it might already be different. Children born the year of its departure would be adults when it reached its destination. Scientists who designed it might never live to see its results. The challenge begins with distance, but it doesn't end there. To send a probe that far, one must first catch the rhythm of the planets, waiting years for a window when gravity assists can slingshot the craft along its path. Even then, the speed we can currently achieve, tens of thousands of kilometers per hour, feels almost motionless compared to the scale ahead. A journey to Uranus is not a sprint, it's a slow drift through eternity. Voyager 2, our only emissary to the ice giants, launched in 1977 and reached Uranus in 1986, nearly a decade later. But Voyager didn't stop. It couldn't. It was built to fly by, not to orbit. To actually stay, to study Uranus up close for years, we would need far more energy we don't yet know how to provide efficiently. Chemical rockets, our current engines, simply don't carry enough fuel to break at the end of such a long journey. So we dream instead of nuclear propulsion, ion engines, or solar sails, technologies that could one day make the outer solar system accessible not just to visitors, but to explorers who stay. But even with the best of today's propulsion, a mission to Uranus would be slow and solitary. The spacecraft would coast through vast darkness for more than a decade, powered by plutonium heat and guided by faint radio whispers from Earth. Each update would take nearly 3 hours to arrive, each photograph days to transmit. The spacecraft would become a traveler between epochs, launched by one generation, received by another. Scientists understand this. They plan accordingly. A Uranus mission would be built not only with technology, but with faith. Faith that the world will still care when the data begins to arrive. Every mission beyond Jupiter is a gift we leave for the future, a message in a cosmic bottle drifting toward its destination. And yet, the waiting is part of the wonder. There's something profoundly human about sending a small machine across billions of kilometers of emptiness, knowing that it will outlive its makers. It's an act of patience, of hope, of continuity. When the probe finally arrives, it will speak for those who dreamed it into existence, and for all of us who ever looked up and wondered what lies beyond Saturn's golden rings. In that sense, the journey to Uranus is more than travel. It's a reflection of ourselves. It shows how far curiosity can reach, even when flesh and bone cannot. It's a reminder that discovery doesn't need to be fast to be meaningful. 15 years to arrive, decades to explore, centuries perhaps, for the knowledge to ripple through humanity. The voyage to Uranus is not just a mission, it's a message across time, sent from one era of dreamers to the next. Temperatures near Uranus drop to negative 224 degrees Celsius. At such extremes, metal becomes brittle, electronics fail, and propellant freezes solid. To travel to Uranus is to send a machine into an environment no human technology has ever truly endured. The cold there is not the kind that bites, it's the kind that erases. It seeps into every wire, every panel, every circuit, until the boundary between solid and fragile disappears. In that deep, airless silence, even the strongest alloys begin to weaken. Plastic cracks, metal stiffens. Batteries lose their will to work. Every movement becomes a risk. Every vibration a potential fracture. For a spacecraft, heat is life. Even in the shadowed vastness of space, our probes carry small nuclear hearts, radioisotope thermoelectric generators, or RTGs, that convert the decay of plutonium into warmth and power. But near Uranus, that faint warmth is swallowed by the cold like a candle in a glacier. The external sensors, cameras, and antenna must endure temperatures colder than liquid nitrogen, where every breath of heat radiates away into nothing. It is the point where human engineering meets the edge of physics. A battle not against time or speed, but against the absence of warmth itself. Electronics are particularly vulnerable. Circuits rely on movement, electrons flowing like a current of light through narrow channels. At negative 224 degrees Celsius, that current slows, resistance rises. Materials that once carried signals easily begin to falter. Even the glue that binds circuit boards can crack under thermal stress, breaking delicate connections designed to last decades. At such temperatures, everything wants to stop moving. Even electricity seems to hesitate. Propellants, the fuels that steer and stabilize a spacecraft, can also freeze solid. Hydrazine, a common maneuvering fuel, turns to ice at negative 220 degrees Celsius. Ammonia-based coolants freeze even sooner. To survive near Uranus, every system must be insulated, every tank warmed, every line monitored constantly to prevent the cold from creeping inward. For Voyager 2, this meant clever engineering, using its instruments and systems like a thermal orchestra, turning components on and off in just the right sequence to keep itself alive. It was a balancing act that had no margin for error. Even communication is tested. The vast antennas on Earth, the deep space network, must detect faint radio whispers from a probe billions of kilometers away. The signal is weaker than the static between radio stations, and in the cold, even the spacecraft's transmitters lose efficiency. Power must be rationed, systems cycled, instruments put to sleep, not because they're broken, but because survival demands stillness. This is the reality of the outer solar system, a place where exploration slows to a crawl and endurance becomes the measure of success. Every mission that reaches beyond Saturn is an act of technological defiance, a refusal to let cold define the limits of curiosity. And yet, Perhaps the most haunting truth is that the cold near Uranus is not empty. It's full of pressure, of silence, of the faint glow of methane clouds and the distant heartbeat of sunlight that took hours to arrive. It's a living cold, one that shapes everything it touches, a sculptor of stillness, carving even machines into forms of patience. For humanity, surviving there means building not just stronger technology, but more resilient dreams. Because in the end, every spacecraft that ventures toward Uranus carries not just instruments, but the warmth of its makers, a fragile spark of Earth's heat, traveling across billions of kilometers of frozen night, daring the universe not to extinguish it. Between Jupiter and Uranus lies a vast region of invisible radiation, an ocean of charged particles that can erase data and fry instruments in minutes. It's a place without light, without sound, and yet full of fury. In this invisible sea, atoms are stripped bare, and electricity flows freely through the void. These are the cosmic shoals of the outer solar system, where Jupiter's immense magnetic field stretches outward like a storm made of energy. Every spacecraft that dares to pass through must survive this gauntlet, an unseen storm that makes metal hum, memory blur, and sensors fail. Jupiter, the largest planet, is also the most dangerous neighbor in space. Its magnetosphere, a magnetic bubble larger than the Sun, traps charged particles from the solar wind and accelerates them to near-light speed. The result is a zone of radiation more intense than anything around Earth. Within this field, electrons and ions whip around like invisible bullets, slamming into any object that enters their path. For a spacecraft, that means every circuit, every chip, every memory bank must be shielded, hardened, or sacrificed. When Voyager 2 crossed this region on its journey to Uranus, it passed through radiation so powerful it nearly overwhelmed its instruments. Memory bits flipped randomly, images corrupted mid-transmission. Engineers on Earth watched as data streams came in filled with noise, the electronic version of static in a thunderstorm. Yet somehow, through careful design and a measure of luck, Voyager endured, using layers of aluminum shielding and sheer resilience to survive the invisible onslaught. But the danger didn't end with Jupiter. The entire space between the gas giants is a diffuse ocean of radiation, shaped by the solar wind, stirred by the magnetic fields of planets, and threaded with cosmic rays from distant stars. It's not a continuous storm, but a shifting maze of danger. A spacecraft traveling through it must navigate zones of higher and lower intensity, timing its journey like a sailor catching favorable tides. Too close to Jupiter, and it's bathed in lethal radiation. Too far from the Sun, and power becomes scarce, the craft too cold to respond. For human explorers, such a region is beyond survivable. The doses of radiation would destroy human cells within hours. Even machines struggle, their microchips eroded by the constant bombardment, their memories rewritten by cosmic interference. Modern probes like Juno, orbiting Jupiter today, must carry nearly 200 kilograms of titanium shielding just to survive, a floating vault designed to protect delicate electronics from the wrath of a planet that never sleeps. To reach Uranus means to pass through this cosmic crucible. It's not just distance that defeats us, but endurance. The slow attrition of invisible forces that wear away at machinery like wind on stone. Space isn't empty, it's alive with energy, unpredictable and relentless. And yet, within that radiation storm lies something beautiful. Those same charged particles, when they strike a planet's magnetic field, create auroras, curtains of light that ripple across poles in silent, shimmering waves. Every glow of green or violet across Jupiter or Saturn is born from that same chaos, transformed from destruction into beauty. For any future mission to Uranus, this maze will remain the first great trial. The passage between the inner worlds of light and the outer realms of shadow. It is the cosmic firewall between what we can visit easily and what still lies beyond reach. Every time a probe crosses it, we learn something profound, that the path to discovery is never gentle. It winds through storms we cannot see and dangers we can only endure, a reminder that even in the emptiest places, the universe still burns. At Uranus's distance, sunlight is 400 times weaker than on Earth. Solar panels barely function. To survive, probes must rely on rare nuclear fuel that's running out. Far from the warmth of the sun, light itself begins to fail. The soft blue glow that bathes Uranus is not true daylight, but the echo of a dying beam. Sunlight stretched thin by distance. For any spacecraft sent there, this fading light is not poetic metaphor, it's a literal crisis. Solar energy, the lifeblood of most modern probes, dwindles to almost nothing in the outer solar system. By the time sunlight reaches Uranus, each square meter of solar panel receives only a fraction of the energy that Earth does, not enough to power even a light bulb. That's why Voyager 2, and every spacecraft to venture beyond Jupiter, has carried its own small star, a radioisotope thermoelectric generator, or RTG. These nuclear batteries don't rely on sunlight. Instead, they draw warmth from the slow, steady decay of plutonium-238, converting that heat into electricity. It's this quiet internal fire that keeps instruments alive, heaters running, and transmitters whispering back to Earth from billions of kilometers away. But plutonium-238 is rare, vanishingly so. It doesn't occur naturally in usable amounts on Earth, and it can't be recycled from nuclear reactors. It must be created in laboratories, atom by atom, through complex and costly processes. And for decades, production nearly stopped. As a result, humanity now has enough plutonium to power only a handful of future missions. Every RTG built is a treasure, a carefully rationed ember meant to keep exploration alive just a little longer. For Uranus, that scarcity is a barrier as daunting as distance itself. A mission there would require not one, but several RTGs to power instruments, maintain heat, and keep communication alive during the long, cold voyage. The farther it travels, the less energy the generator produces, as the plutonium decays and heat output declines. By the time it arrives, after 15 years or more, the probe will already be dimmer than when it left, its strength fading even before its journey truly begins. Solar power, our clean and endless energy source, offers no solution. Even the most advanced arrays, like those on the Juno mission to Jupiter, barely function in that realm of weak light. At Uranus, they generate less than 1% of their Earthside power, their panels needing to be the size of football fields just to operate a few instruments. The cold alone would make them brittle, the darkness too deep to sustain them. So our dreams of exploring the ice giants rest on a dwindling stockpile of radioactive metal, forged by human hands but limited by time and will. Each mission becomes a negotiation between curiosity and scarcity, which worlds deserve the last sparks of our nuclear light. And yet, this problem holds a strange kind of poetry. Every probe that drifts through the dark carries within it a fragment of fire, the same fire that once forged stars, now repurposed to illuminate their remnants. When a spacecraft crosses the void between Saturn and Uranus, that tiny ember is all that stands between existence and oblivion. If we ever solve this problem, if we learn to harness fusion, antimatter, or some yet unknown energy, Uranus will be waiting. Until then, the planet remains wrapped in blue silence, orbiting a sun too distant to touch, its mysteries dimly lit by the last fading sparks of human ingenuity. In the end, the problem of power isn't just about technology, it's about endurance. The isotope plutonium-238, which powers deep space missions, is so scarce that NASA only has enough left for 1 or 2 future explorers. It is, quite literally, the fire that keeps our dreams alive, a material so rare that it may determine the limits of where humanity can go. Without it, the farthest worlds, Uranus, Neptune, and the edges beyond, remain unreachable. Plutonium-238 is not the stuff of weapons or reactors. It's a gentle isotope, its warmth born from slow radioactive decay, releasing heat steadily for decades. It's what powered Voyager 2 as it drifted through the dark. It's what lights the Curiosity rover on Mars, still driving after more than a decade. And it's what any probe bound for Uranus would need just to survive the cold. But we are running out. For decades, the United States produced no new supply. The Cold War ended, demand vanished, and with it, the infrastructure that once sustained the isotope's creation. The last large batch was made in the 1980s, around the same time Voyager was passing Uranus. What remains now sits in carefully guarded storage, measured in kilograms rather than tons. Enough to power perhaps 2 more major missions. After that, the furnaces of deep space will go dark. Plutonium-238 can't be mined. It must be made, coaxed into existence in reactors that bombard Neptunium targets with neutrons. The process is slow, expensive, and delicate. In recent years, NASA and the Department of Energy have restarted small-scale production, yielding just a few hundred grams per year. But it's not enough. At this pace, each new deep space mission becomes a question of priority. Which world gets the last ember? Uranus? Neptune? A return? To Titan? Or perhaps a probe sent beyond the heliosphere to the interstellar night? The irony is profound. Humanity has no shortage of energy. We can split atoms, harness stars, even imagine fusion drives. But the specific isotope that allows us to explore the coldest, darkest corners of the solar system is rarer than gold. Each gram is priceless, not for what it is, but for what it makes possible. Motion through emptiness, warmth in absolute zero. Life for a lonely machine drifting where sunlight cannot follow. Imagine the moment a spacecraft arrives at Uranus, its RTG faintly glowing with heat that left an Earth-bound reactor 20 years earlier. That same warmth will still be there decades after launch, a small, steadfast pulse against the cold. It's the closest thing to a heartbeat a machine can have. Without plutonium-238, that heartbeat stops. The silence of Uranus would remain unbroken. This vanishing isotope has become a symbol of a larger truth, that exploration depends not only on ambition, but on materials that tie us physically to the cosmos. Each atom of plutonium is a promise, a fragment of Earth that carries human hope across billions of kilometers. And as the supply dwindles, the question deepens. When the last capsule of plutonium is sealed into the last RTG and the final deep space probe leaves Earth, what happens next? Will we find a new way to kindle light in the dark, or will the universe reclaim its silence, waiting for us to reignite the stars within ourselves? Uranus's low gravity and lack of solid surface make landing impossible. Any probe descending into its atmosphere would sink endlessly until it's crushed or melted away. There is no ground on Uranus, no surface to stand on, no horizon to reach. The planet looks solid from afar, its pale blue skin, serene and uniform. But it's an illusion. Beneath those calm clouds lies not land, but layer upon layer of gas and ice, a slow descent into pressure, darkness, and heat. To fall toward Uranus is to fall forever. If a spacecraft entered its upper atmosphere, the journey would begin gently. The first few hundred kilometers would feel calm, a drifting through pale mist, methane clouds, and a cold so deep it would freeze air itself. But soon, the descent would accelerate. Pressure would build, density would rise, and the temperature would begin to climb. The clouds would thicken into fog, the fog into fluid, and then the atmosphere itself would become something stranger, neither gas nor liquid, but a crushing ocean of supercritical ice and hydrogen. A probe sent into Uranus, like Galileo's probe that once dove into Jupiter, would have no chance of survival. Its instruments would record pressure, temperature, and composition as long as they could, perhaps for an hour, maybe 2, before the weight of the atmosphere crushed it like paper. At 10 times Earth's pressure, steel buckles. At 100 times, even titanium yields. And deeper still, the heat grows fierce. Methane breaks apart, carbon crystallizes, and the theoretical diamond rain begins. The probe would fall through glittering storms into a region where physics itself starts to twist. There is no solid core in the sense we understand. Scientists believe that deep within Uranus, gases compress into exotic forms, water and ammonia crushed until they behave like metals, conducting electricity in ways no earthly material can. Below that, perhaps, lies a small rocky core, no larger than Earth but buried beneath tens of thousands of kilometers of liquid ice and superheated gas. No machine has ever seen it, and none ever will. This is the cruel paradox of gas and ice giants. They invite exploration but deny arrival. There's nothing to land on, only depths to drown in. A probe that enters Uranus's clouds does not touch down. It disappears, swallowed by gravity and pressure until it ceases to exist. Even if it were armored with the strongest materials known to science, the increasing density and temperature would melt it, vaporize it, and scatter its atoms among the storms. Uranus's gravity is deceptive. It's lower than Earth's at the cloud tops, only about 90% as strong, but it's relentless. There's no friction to slow a fall, no ground to stop it. Gravity doesn't just pull you down, it invites you in, deeper and deeper, until you become part of the planet itself. To land on Uranus, then, is to surrender to it. To let go of the idea of a surface, of up and down, of boundaries at all. A descent into Uranus would be a descent into abstraction, a slow dissolve from machine into molecule, from matter into myth. It's fitting, in a way. Uranus, the sideways planet, breaks the rules of structure and form, just as it breaks the rules of light and magnetism. It is not a world of surfaces, but of continuums, an endless gradient from sky to core. And so it waits, untouchable, a giant without a flaw, holding its secrets beneath clouds we can only ever skim, never truly enter. A reminder that not all mysteries are meant to be stood upon. Some are meant only to be admired from the edge and imagined in the silence beyond. Beneath the clouds, there is no ground, only denser and denser gas. A falling spacecraft would drift downward forever, crushed before ever touching surface. Imagine falling through a world with no end. The descent begins softly, gently. A slow drift through clouds the color of smoke and ice. The sunlight fades behind you, filtered through methane haze until even its blue turns to grey. Below, there are no landmarks, no shapes to guide you, only fog, pressure, and the growing whisper of gravity pulling you into the deep. At first, the air is thin, a faint chill, molecules sparse and quiet. But with every kilometre you fall, the atmosphere grows thicker, heavier, more relentless. Your instruments begin to groan. The soft hydrogen and helium you drift through become dense enough to press against you like a liquid. Pressure builds to 10 times, then 100 times that of Earth's atmosphere. The walls of your craft shudder. Every bolt, every seam begins to ache under the invisible weight. And still, you keep falling. No ground rushes up to meet you, only more air, more gas, more layers of methane and ammonia swirling in slow-motion storms. The clouds begin to flash with distant lightning, bursts of electric fire that illuminate your descent for an instant before vanishing into black. You pass through what could be oceans of slush, water and ammonia, mixed in states that defy definition, neither solid nor liquid, but something in between. The boundaries blur, above and below lose meaning. You fall for hours, maybe days, and still you are nowhere near the core. The pressure outside is now hundreds of thousands of times greater than what your body could withstand. The temperature climbs past 1,000 degrees. Hydrogen begins to behave strangely, no longer a gas, but a metallic fluid, conducting electricity like molten silver. In that moment, your descent passes the point where matter behaves like matter. Physics itself starts to shimmer at the edges. No probe has ever reached this far, none ever will. A spacecraft entering Uranus's depths would be crushed long before it could glimpse what lies beneath. Even its radio signals, those last desperate whispers to Earth, would be absorbed by the dense atmosphere, fading to static before ever escaping. what happens deeper still is beyond imagination. The deeper you go, the slower time seems to move. Heat and pressure merge into something closer to energy than matter. There may be a rocky core, or there may not. There might only be motion, an eternal churn of hydrogen and ice, mixing endlessly for billions of years. To fall into Uranus is to surrender the idea of arrival. There is no destination waiting at the bottom, no solid ground, no alien landscape. Just the continuation of descent, until the concept of down itself dissolves. The deeper you fall, the less you exist as yourself. You become part of the planet, atoms scattered among its layers, folded into its gravity. In a way, this endless fall captures the essence of Uranus. A planet defined not by what it shows, but by what it hides. Its beauty is not in its surface, but in its absence of one. It is a world that resists finality, that refuses to be reached. And so the fall never ends. The clouds close behind you, the light fades completely, and the silence becomes absolute. The only motion that remains is gravity itself, infinite, patient, and eternal. Inside Uranus, carbon atoms compress into diamonds that fall like rain, gemstones forming and sinking through metallic seas of ice and water. It sounds like something out of myth, a storm where jewels fall from the sky, where every drop sparkles before vanishing into the dark. But within Uranus, this isn't fantasy, it's physics. Deep beneath the planet's gentle blue clouds, in layers hidden from light, pressure, and temperature climb to unimaginable extremes. Methane, simple carbon and hydrogen, becomes the raw material for a celestial alchemy. As the weight of the atmosphere bears down, the methane molecules begin to break apart. The hydrogen drifts away, light and restless, while carbon remains, squeezed tighter and tighter until it crystallizes. Out of that pressure, pure diamond begins to form, not in mines, not in time spans of centuries, but in moments. Billions of tiny gems materialize in the dark, born from the chemistry of a frozen world. The diamonds fall like snow at first, flakes of light cascading silently through methane clouds. But as they descend deeper, they merge into larger, heavier pieces, tumbling through the dense fluid layers below. Each gem gleams for a moment as it catches a flash of lightning or the faint shimmer of refracted sunlight, and then disappears forever into the black. Scientists believe these diamond storms may continue for thousands of kilometers below the clouds. At greater depths, where temperatures rise to thousands of degrees, the falling diamonds may melt again, forming an ocean of liquid carbon, a sea of shimmering metallic diamond rain. Some may even settle onto a diamond crust around the planet's deep core, a glittering layer that has existed for billions of years, unseen, untouchable. This process doesn't just make Uranus beautiful, it might help explain its mysteries. The diamonds, as they fall, carry heat deeper into the planet, trapping it instead of letting it escape. That could be why Uranus radiates so little warmth compared to other giants. Its own beauty is its burden, a world cooled by the glittering rain it creates. The evidence for this phenomenon began not in space, but in laboratories on Earth. Scientists used lasers to recreate the intense pressures inside Uranus, compressing methane until it transformed. For an instant, within a tiny chamber, real diamonds formed, proof that the impossible storms of the ice giants might indeed be real. Imagine, for a moment, standing above those clouds, though no human ever could, and seeing flashes deep within, like faint lightning beneath blue glass. Each spark might mark another diamond forming, another stone beginning its slow descent into the unknown. Beneath that serene exterior, Uranus hides storms of unimaginable beauty, violence, and elegance, bound together in eternal fall. The diamond rain of Uranus is more than a scientific curiosity. It's a reminder that even in the coldest, most distant places, the universe still finds ways to create brilliance. Beauty does not need sunlight to exist. Sometimes, it's born in darkness, under pressure, falling silently into infinity. And somewhere, Deep within that blue giant, 1,000 trillion diamonds continue to fall, unseen, unending, and eternal, glimmering in the dark heart of a world that never stops dreaming. Below the atmosphere may lie a global ocean of exotic fluids, water, methane, and ammonia, behaving not as liquids, but as supersonic ice, glowing and conductive. It is an ocean unlike any ever known, not blue, not reflective, not calm. Imagine a sea where the waves are made of ice that flows like molten glass, where lightning arcs beneath the surface, and where pressure turns ordinary matter into something extraordinary. Deep inside Uranus, beneath its tranquil clouds, lies this alien realm, an ocean that blurs the boundaries between solid, liquid, and plasma. Here, water does not behave like water. At pressures millions of times higher than Earth's atmosphere, and temperatures reaching thousands of degrees, molecules are torn apart. Hydrogen atoms drift freely through a crystalline lattice of oxygen, a strange state of matter known as supersonic ice. It is neither fully solid nor fluid, but something in between, an ice that conducts electricity, glowing faintly from within as charged particles move through it. For decades, this was theory. A mathematical curiosity born from computer simulations and the need to explain Uranus's strange magnetic field. Unlike Earth's neat, centered magnetosphere, Uranus's magnetic field is tilted wildly, lopsided, and off-center. It seems to wander as the planet rotates, like a compass that refuses to stay still. Scientists eventually realized that such chaos could only come from deep within, from a vast, uneven layer of conductive material twisting slowly around the planet's core. That layer, they believe, is this global ocean of supersonic ice. A shell of glowing water and ammonia hundreds of kilometers thick. It moves sluggishly but powerfully, churning like a slow electrical storm. This inner motion generates Uranus's unstable magnetism, a magnetic field that flickers and sways as though alive. In laboratories on Earth, scientists have begun recreating these same conditions using powerful lasers and diamond anvils. For the briefest moments, they've glimpsed this strange form of ice, opaque, dense, and warm, glowing faintly under immense pressure. It doesn't melt or freeze in any familiar sense. It transforms, existing at the boundary of what we can define. If you could somehow see this ocean up close, though no machine could survive long enough to witness it, it would not look like any ocean on Earth. There would be no light, only a faint luminescence, the glow of electricity sliding through hydrogen like currents through metal. The waves wouldn't ripple, they would pulse. The water wouldn't splash, it would flow in slow, shimmering folds dense enough to drown light itself. It's strange to think that beneath a planet so cold on the outside lies such restless energy within. But that contrast is part of what makes Uranus so enigmatic. Its calm exterior hides an interior alive with movement, glowing seas that generate magnetism, that shape the planet's storms, that may even create the diamond rain above them. We call it an ocean, but it's something more profound, a planetary heart pulsing in slow time, keeping Uranus alive from within. It connects the cold surface to the fiery depths, transforming pressure and darkness into motion and magnetism. Perhaps, one day, a probe will fall deep enough to sense it, to measure its warmth, to hear its electric hum. Until then, the ocean beneath remains one of the solar system's most haunting mysteries. A sea of ice that glows like molten metal, hidden beneath clouds of eternal twilight. It is not water as we know it. It is something beyond, a reminder that even the most familiar elements under the right conditions can become otherworldly. In the heart of Uranus, water itself becomes a star. At depths of thousands of kilometers, pressure is so extreme that atoms themselves deform, creating matter found nowhere else in the solar system. Deep inside Uranus, the concept of matter begins to break down. What we call solid, liquid, or gas no longer applies. The rules that shape our world, gravity, chemistry, even structure itself, begin to blur under forces so immense that atoms are squeezed into forms they were never meant to take. This is the heart of an ice giant, a crucible of pressure so profound it bends reality into something new. Imagine descending through the blue haze, past the diamond storms and the oceans of metallic ice. The deeper you fall, the heavier the weight becomes, not the weight of matter, but the weight of the planet itself, pressing inward from every direction. The pressure rises to millions, then tens of millions, of atmospheres. It is not just enough to crush steel, it is enough to crush the very structure of atoms. In this crushing silence, molecules no longer behave like themselves. Hydrogen atoms are forced so close together that their electrons begin to overlap, forming a new exotic state known as metallic hydrogen, a substance so strange it could conduct electricity better than copper. Around it, water and ammonia no longer flow or freeze. They vibrate in dense, glowing sheets of supersonic ice, flickering with electrical storms that ripple through layers of the planet like silent lightning. This is not the realm of chemistry, it's the realm of quantum mechanics and pressure physics, where the familiar world dissolves into plasma-like layers and matter flows like thought. The atoms that make up your body would be unrecognizable here, their shells crushed inward, their identities stripped away. What remains are pure forces. Protons, electrons, and the fields that bind them, struggling against the weight of an entire world. No machine could survive this descent. The strongest metals would buckle. The densest ceramics would liquefy. Even the theoretical diamond armor of a future probe would crumble into vapor. There is no bottom to reach, no stable layer where a craft could rest. Just pressure, building endlessly, until temperature and density merge into a single violent equilibrium. And yet, this is where Uranus's secrets are forged. The pressure within its heart may explain its tilted magnetism, its faint thermal glow, its strange calmness. Here, inside this unseen realm, elements are remade into something primordial. Matter, as it might have existed in the early universe, before stars ignited, before planets cooled. Scientists can only recreate fragments of this environment in laboratories, tiny flashes that last less than a second. They use lasers and diamond anvils to crush samples to millions of atmospheres, glimpsing new materials that exist only under these impossible conditions. Every experiment feels like eavesdropping on a planet's heartbeat. What happens beyond those pressures remains speculation. Perhaps deeper still, matter fuses into something even more exotic, a soup of free particles, or a crystalline lattice of degenerate matter, like that inside dead stars. It's a strange thought, that inside Uranus, in the coldest planet of our solar system, might dwell the same forms of matter that fill the hearts of suns. The pressure at those depths is not just physical, it's existential. It reminds us that beneath every tranquil surface, the universe hides violence and transformation. That matter itself is flexible, mutable, capable of becoming something else when pushed far enough. Uranus's depths are a lesson in extremes. They show us that even the calmest worlds contain hidden storms, and that beauty and destruction are often the same force, viewed from different depths. There, thousands of kilometers below the clouds, reality doesn't shatter, it reshapes. And in that reshaping, the universe whispers its oldest truth, that nothing, not even atoms, stays the same forever. The planet's distinct blue color comes from methane, absorbing red light and reflecting blue, turning Uranus into a mirror of cold fire. When you look at Uranus through a telescope, what you see is not its surface, not even its clouds, but its reflection, a delicate veil of color shaped by the faintest sunlight reaching the edge of our solar system. Its blue glow is one of the most haunting sights in the night sky. Soft, pale, and almost unreal. It looks like stillness made visible, as if the planet itself were holding its breath. That hue, the icy turquoise that gives Uranus its ethereal presence, comes down to chemistry. In its upper atmosphere, methane gas floats in thin, shimmering layers. When sunlight travels all the way from the sun, nearly 3 billion kilometers through empty space, it arrives weak, faded, and cold. Methane absorbs the red and orange wavelengths of that dying light, allowing only the blues and violets to scatter back into space. The result is a planet that glows not with warmth but with absence, a world painted in the light it refuses. It is a strange kind of beauty, cold fire, born from subtraction. The colour we see is what Uranus gives back after it swallows everything else. It's like looking into the memory of sunlight rather than sunlight itself. The more one studies that glow, the more surreal it becomes. Underneath those layers of methane, the planet may not be blue at all. If the gas were stripped away, Uranus might appear grey or white, its storms and deeper clouds hidden beneath the tinted haze. The blue we see, then, is an illusion, an optical echo of the gases that crown its upper atmosphere. The same light that defines the planet's identity also conceals its truth. And yet, this illusion is what makes Uranus so mesmerizing. Its color shifts subtly depending on where you look. Sometimes turquoise, sometimes aquamarine, sometimes almost silver. High-altitude clouds reflect more light, giving fleeting hints of brightness, while deeper methane layers darken the hue toward the poles. From afar, the planet seems smooth and featureless, but through infrared eyes, swirling storms and faint bands emerge beneath the glassy calm. Beneath serenity lies motion. Beneath light lies shadow. Methane is more than color, it's the atmosphere's storyteller. It drives Uranus's weather, shapes its temperature, and dictates how sunlight interacts with its skies. When lightning flashes deep within its clouds, that same methane ignites in ghostly bursts of violet and blue, illuminating the darkness like a storm made of gemstones. The methane mirror is not just what Uranus looks like, it's what it is. A reflection of distance, of chemistry, of time. The light that leaves its atmosphere takes hours to reach us, and by the time it does, the planet has already turned, changed, shifted. We never see Uranus as it is now, only as it was hours ago, a frozen reflection caught between then and now. And perhaps that's why the planet feels so dreamlike. It doesn't shine with heat like the inner planets, nor with fury like Jupiter. It shines with restraint, with quiet. Uranus glows in the colour of distance itself, a reminder that even in the outer dark, light endures. And sometimes, what's most beautiful about a world is not the light it creates, but the light it chooses to keep. Scientists believe Uranus's strange magnetic field may reverse periodically, collapsing and rebuilding, an invisible heartbeat pulsing through the void. If Uranus could be said to have a pulse, it would not come from sound or motion, but from magnetism, an unseen rhythm deep within its heart. Most planets have magnetic fields that behave like well-ordered systems, steady, aligned, predictable. Earth's field, for instance, flows from a magnetic north to a magnetic south, anchored neatly to its axis of rotation. But Uranus defies this rule entirely. Its magnetic field is tilted 60 degrees away from its axis and shifted far from its center, a chaotic and asymmetric force that seems to move with a mind of its own. As the planet rolls through space, this magnetic field tumbles with it, sweeping and twisting like a cosmic kaleidoscope. In some regions, magnetic lines converge. In others, they vanish completely. The field doesn't wrap around the planet evenly. It flickers, pulses, and drifts, as if it were breathing. To scientists, this strange behavior suggests something extraordinary. Uranus's magnetosphere may periodically collapse and rebuild itself, reversing polarity in cycles that last only days or weeks. Imagine that, an entire planet's magnetic field flickering in and out of existence, reconfiguring itself like a living organism adjusting its heartbeat. One moment, the planet shields itself from the solar wind. The next, it opens wide, letting charged particles flood in. Auroras, those ethereal curtains of blue and green light, flare unpredictably across its poles, shifting position and intensity as the field reshapes itself. No one knows exactly why this happens, but deep beneath the clouds, the answer likely lies in motion. Uranus's interior isn't a solid iron core like Earth's, nor a molten metallic sea like Jupiter's. Instead, it contains a vast convective layer of superionic water and ammonia, fluid, conductive, and constantly in flux. As this material churns, it generates magnetic fields, but because the layer is uneven and offset, the result is chaotic. The magnetic poles wander, twist, and sometimes even invert. Uranus's field may not just be strange, it may be unstable by design. Voyager 2's instruments detected the first hints of this mystery during its flyby in 1986. The data revealed abrupt changes in the magnetosphere's shape, bizarre pulsating distortions that seem to occur over short timescales. Later simulations suggested what those readings implied. Uranus's magnetic field may not be static at all. It may be dynamic, flickering in a pattern that no other planet follows. This revelation changes everything. Magnetic fields aren't just invisible forces, they shape how a planet interacts with space. They protect atmospheres from the solar wind, influence weather patterns, and create the auroras that shimmer at night. If Uranus's magnetosphere is collapsing and rebuilding constantly, it means the planet's environment is alive, constantly rewritten by its own magnetic chaos. And what's most haunting is the thought that this heartbeat might not be unique. Other ice giants, like Neptune, may share this strange rhythm, their magnetic fields rising and falling in cycles we cannot yet measure. They are worlds whose very essence is unstable, always in motion, always reinventing themselves. To call it the lost magnetic field is perhaps fitting. It's not lost because it's gone, but because it refuses to stay found. It vanishes, returns, flickers in the dark, a reminder that even in the farthest reaches of the solar system, life and death, order and chaos repeat in endless rhythm. Somewhere, right now, deep beneath Uranus's blue clouds, that invisible pulse continues, an electromagnetic breath that no one can hear, but that shapes the world around it. A heartbeat echoing through the void, felt only by the machines that once dared to listen. The planet's 98-degree tilt creates bizarre seasons where one pole bakes in sunlight for decades while the other freezes in eternal night. Uranus doesn't just orbit the sun, it rolls around it. Its axis is tilted so dramatically that it spins almost completely on its side, like a marble tipped over mid-spin. No other planet in the solar system behaves this way. Where Earth tilts a gentle 23.5 degrees, giving us our familiar cycle of seasons, Uranus leans at nearly 98. That single angle changes everything. It turns the planet's year into a cosmic paradox, a dance of light and shadow that stretches across centuries. A year on Uranus lasts 84 Earth years. For nearly half that time, one hemisphere faces the sun continuously, while the other lies in absolute darkness. Imagine standing near the North Pole of Uranus during its long summer. The sun would hang in the same spot in the sky, circling but never setting, blazing weakly through the methane haze for over 40 years. Then, as the planet continues its slow orbit, that same pole would fade into winter, darkness so complete that dawn wouldn't return for another 4 decades. This endless seesaw of light and cold shapes everything about Uranus's atmosphere. The planet's weather patterns are unlike any others in the solar system. When the seasons shift, entire hemispheres heat and cool on scales that defy intuition. Winds reverse direction. Storms awaken, then vanish into silence. The upper atmosphere brightens with faint auroras and hazy methane clouds that drift for years before dispersing. Even the planet's delicate rings may respond to this slow turning, glowing faintly in reflected light before fading back into the dark. Scientists believe that this extreme tilt may have been caused by a catastrophic event billions of years ago, perhaps a collision with a planet-sized object. Such an impact could have knocked Uranus onto its side, shattering its original symmetry and forever altering its destiny. It may also explain why its magnetic field is so chaotic and off-center, a lingering scar of that cosmic upheaval. From afar, the tilted world looks calm, serene, and slow. But beneath that stillness lies a planet constantly out of balance, struggling to redistribute energy across hemispheres that alternate between eternal day and endless night. Each season lasts longer than a human lifetime. A storm that begins in one era may only dissipate in the next. Time itself stretches differently there. Motion becomes memory. It's difficult to imagine what weather means on such a world. During the long night, the temperature plunges toward absolute zero. Methane clouds condense and fall. Lightning flickers through the dark like faint veins of blue fire. Then, as the sun's faint light returns decades later, the ice and gases awaken again, swirling into new patterns, new tempests, new forms of motion. Uranus's tilt turns it into a living paradox, a planet frozen and burning at once, its hemispheres locked in a slow cosmic exchange. One side sleeps, while the other dreams. One end of the world lives in sunlight, while the other forgets what light feels like. If Earth's tilt gives us the rhythm of days and years, Uranus's gives it something deeper, a cycle of transformation that unfolds on a timescale far beyond human experience. Each dawn, each dusk, each season is a generational event. It is, in every sense, the cosmic tipping point, a reminder that even in the clockwork order of the solar system, there are worlds that spin to a stranger rhythm. Worlds where time bends, light lingers, and the very idea of a day loses meaning beneath an endless twilight sky. For much of its orbit, Uranus never truly experiences day or night, only a perpetual gradient of pale light and indigo shadow. If you could drift above Uranus's clouds, you would never see a sunrise in the way we know it. The sun would not rise or set, it would merely fade, a distant spark swallowed by mist. The planet's extreme tilt and slow orbit conspire to erase the ordinary rhythm of light and dark. For decades at a time, half of Uranus is trapped in shadow, while the other half bathes in unending daylight. And yet, at the equator, there exists a haunting in between, a realm of permanent dusk, where the light is never gone, but never whole. This twilight is not the warm amber of an earthly evening, but something colder, lonelier. The sunlight that reaches Uranus has travelled nearly 3 billion kilometres, weakened until it feels more like memory than illumination. It spreads through methane haze, scattering into shades of ghostly cyan and deep indigo. Even at its brightest, the light here is dimmer than a sunset seen through storm clouds. And when darkness falls, it's not black, it's violet, streaked with faint glows from auroras and lightning buried far below. The boundary between day and night stretches across thousands of kilometres, a soft, endless gradient of colour. Clouds drift through it like shadows crossing ice. The winds here are slow, heavy with methane crystals, whispering across the upper atmosphere in currents that last for centuries. There are no sharp contrasts, no moments of change, only transition itself unfolding forever. This perpetual twilight might be the closest thing in the solar system to stillness. There are no days to mark time, no stars visible through the haze, no sunrise to promise renewal. Only the slow rotation of a planet that has turned on its side, and the faint glimmer of a sun too far away to warm it. Even time feels slower here, stretched by distance and dim light. A second feels longer when there is no clear distinction between before and after. And yet, this dimness holds its own kind of beauty. Look closely, and the light reveals subtle textures, thin bands of cloud wrapping around the planet like silk, faint lightning flickers glowing deep within, hints of turquoise swirling in the cold mist. Uranus is not empty, it's quiet. Its light is not gone, it's resting. In this world of soft gradients, contrast has no meaning. There is no bright, no dark, only degrees of serenity. The sky glows as though the entire planet were suspended between dawn and dusk, between motion and stillness, between presence and memory. Perhaps this eternal twilight mirrors something in us, a yearning for balance between chaos and calm, between discovery and rest. A reminder that not all light must blaze, and not all darkness must consume. Uranus drifts through the outer solar system as a planet caught between extremes, illuminated by a sun that can barely touch it. Its skies are neither day nor night, but something more subtle, an everlasting in-between, where time dissolves and the universe seems to pause to catch its breath. The planet of eternal twilight doesn't shine like a beacon. It glows like a thought, lingering softly at the edge of consciousness. Far above the clouds, Uranus glows with faint auroras, green and violet curtains of light flickering in silence, never seen by human eyes directly. These lights are the planet's quietest voice, whispering to the void through color instead of sound. They dance not for an audience, but for the rhythm of the universe itself, a luminous pulse that speaks of magnetism, solar winds, and the invisible architecture of space. On Earth, auroras roar across polar skies in vibrant greens and reds, visible to anyone standing beneath the right darkness. But on Uranus, there is no atmosphere thin enough, no human presence to watch. Its auroras bloom in a vacuum of silence, high above its methane haze, their radiance too faint to pierce the blue clouds below. Only our instruments, radio telescopes, and far-off spacecraft have detected their existence, tracing their ghostly arcs across the planet's poles. Unlike Earth's steady curtains of light, Uranus's auroras behave unpredictably. Because its magnetic field is tilted and off-center, the poles of magnetism don't line up with the poles of rotation. The result is a constantly shifting stage. As Uranus spins on its side, its magnetosphere wobbles wildly, sweeping its auroras across unexpected latitudes. Sometimes they encircle the planet like glowing rings. Sometimes they appear at mid-latitudes or drift toward the equator. They are lights without fixed geography, drifting like thoughts through the atmosphere. Each flare of auroral light is a meeting of forces, solar particles from the Sun colliding with the gases of Uranus's upper atmosphere. Hydrogen and helium, normally invisible, shimmer briefly when struck by these charged winds, releasing light in wavelengths we can barely see. The hues are strange and subdued. Emerald fading to lavender, violet giving way to icy blue. Their silence is total. No sound, no echo, just the faint pulse of energy releasing itself into emptiness. For a moment, as those particles strike and glow, the darkness above Uranus becomes alive. Magnetic lines reconnect and twist. Energy arcs through the atmosphere, and a ghostly shimmer appears, fleeting, delicate, and eternal. The light may last seconds or minutes, but its memory lingers across the magnetosphere like ripples through water. Scientists studying these auroras have discovered that they may hold secrets to Uranus's chaotic magnetic field. Each flicker, each flash, traces the invisible structure of the planet's magnetosphere as it interacts with the solar wind. In these lights, we can glimpse the heartbeat of the planet, its electromagnetic breath captured in color. And yet, there is something haunting in knowing that no human will ever stand beneath those skies to see them directly. The auroras of Uranus burn unseen, performing in solitude. They exist purely for themselves, for the quiet mathematics of plasma and magnetism. Imagine them from afar, thin veils of light winding through infinite darkness, illuminating a world too cold for life, too distant for sound. Curtains of cosmic fire that ripple in perfect stillness, like lanterns drifting on an invisible sea. In the grand theatre of the solar system, Uranus's auroras are the faintest notes in a vast cosmic symphony, soft, elusive, and profoundly serene. They remind us that even in silence, even in the coldest corners of existence, the universe still finds ways to glow. To send a human mission would require more fuel than we could ever carry, and more time than a human lifetime can endure. Uranus isn't just distant in space, it's distant in possibility. The dream of sending humans there belongs to an era that has not yet come, an age when propulsion will be more than chemical fire and patience. For now, the planet remains the unreachable horizon, glimmering faintly in the cold dark, waiting for a kind of traveler that does not yet exist. To reach Uranus, a spacecraft must cross 3 billion kilometers of emptiness. Every kilometer adds weight, not just of distance, but of energy. Every meter per second of speed requires more fuel than the last. A ship large enough to carry humans and life support systems could never accelerate fast enough, or slow down safely once it arrived. Even with gravity assists and decades of planning, the fuel requirements exceed anything our species has ever launched into space. But the problem is not only one of distance, it's one of time. A mission to Uranus using today's fastest propulsion would take around 15 years just to arrive. By then, the crew would have lived a quarter of their lives in transit. A round trip could consume half a century. Generations might pass before the explorers who left Earth could see home again, if they ever could. Radiation, isolation, and the absence of sunlight would turn such a journey into an odyssey of endurance. The astronauts would live in the dim glow of artificial light. Their days measured not by sunrise, but by the ticking of systems designed to keep them alive in a vacuum. Outside, there would be nothing. No stars bright enough to comfort, no blue earth rising in the window, only the constant hum of machinery and the infinite silence of space. Even if we solved the problem of distance, the destination itself would resist us. There is nowhere to land, no ground to stand on, only crushing gases and impossible cold. A human mission to Uranus would not end with a footprint. It would end with orbit, observation, and eventually, silence. The planet offers no home, no refuge, no promise of return. It is a destination without arrival. And yet, there is something profoundly magnetic about that impossibility. Uranus draws our imagination the way a horizon draws a traveler. The very fact that it is unreachable makes it alluring. It is the gravity of the unknown, the pull of mystery itself, that tugs at us. Every great act of exploration begins with a world we cannot yet touch. The Moon was once that world, so was Mars. Each step outward begins as a dream beyond reason, a calculation that doesn't balance until new technology and new courage arrives. One day, perhaps, humanity will look back at Uranus not as the edge of reach, but as another chapter in the long story of curiosity. Perhaps nuclear fusion, antimatter drives, or light sails will carry us there. Perhaps generations born aboard interstellar ships will know the pale blue light of Uranus, not as a dot in the sky, but as a neighbour. But for now, it remains untouchable, a world that humbles ambition and reminds us of scale. The gravity that holds Uranus in orbit around the Sun is the same gravity that holds our wonder in place, pulling our eyes upward, urging us to dream further, even when we cannot go. Because in the end, the gravity of the unknown is not a force that keeps us from reaching, it's the very thing that makes us try. Even if we could travel there, the energy needed to slow down and enter orbit safely would exceed any technology humanity currently possesses. In the grand theatre of space travel, distance is not the only barrier, momentum is. Every spacecraft that leaves Earth is bound not just by how fast it can go, but by how precisely it can stop. To reach Uranus is one thing, to stay there is another. It is a paradox that defines deep space exploration. The faster you go, the harder it becomes to slow down. A probe bound for Uranus must first accelerate to tens of thousands of kilometers per hour, riding the gravity of planets like Jupiter to build speed. But when it finally reaches its destination, that velocity becomes a curse. To enter orbit, it must shed nearly all of it, otherwise it will simply slingshot past the planet and vanish into the outer dark. And at nearly 3 billion kilometers away, there's no second chance, no rescue, no do-over. The braking burn required to capture a spacecraft around Uranus would demand a level of energy almost equal to that used to launch it from Earth. For a robotic probe, this already borders on impossible. For a human mission, it's unthinkable. We simply don't possess propulsion systems efficient enough to carry both the fuel to accelerate and the fuel to decelerate. Even nuclear-powered engines, our most advanced theoretical designs, would struggle to balance that equation. This is what physicists call the tyranny of the rocket equation. It governs every journey we make into the cosmos. The more fuel you need for slowing down, the heavier your ship becomes. The heavier your ship becomes, the more fuel you need to launch it. The equation feeds on itself endlessly, demanding exponential increases in energy for each extra ton. By the time you calculate the fuel required to reach Uranus and return safely, the numbers collapse under their own gravity. That's why Voyager 2 never stopped. It wasn't designed to. It raced past Uranus at over 15 kilometers per second, too fast to be captured, too precious to slow. In a sense, that's how all our deep space missions have survived, by never stopping, by trading permanence for discovery. Even with future propulsion, fusion drives, ion sails, or antimatter engines, the challenge remains daunting. Slowing down requires energy, and energy requires mass, and mass defies speed. Unless we invent a form of propulsion that breaks free from this chain, something like space-time manipulation or external energy harvesting, Uranus will remain a flyby world, a place we can only glimpse while passing through. But perhaps that limitation is part of the beauty. Physics reminds us that the universe is not cruel, it's consistent. The same laws that hold us back are the ones that make the cosmos predictable, stable, and comprehensible. They're the reason stars burn and planets orbit, the reason we can even imagine the impossible. To stand at the edge of what physics allows is to stand at the edge of meaning itself. Each new discovery stretches that boundary a little further, but never without cost. The very fabric of reality seems to whisper, "You may go this far, but no farther, not yet." And so, Uranus waits behind a wall not of distance, but of equations, numbers that bind us as firmly as gravity itself. We can see it, model it, even send our machines to glance its way. But to reach it, to stay there, to orbit and understand it in person, those dreams still lie beyond the limits of energy, mass, and time. Perhaps one day we'll rewrite those limits. Perhaps the laws that now forbid us will one day guide us instead. But until then, Uranus remains what it has always been. A cold blue truth at the edge of what physics permits. A silent reminder that the universe's greatest mysteries endure not because they are hidden, but because they are honest. In the time it would take to reach Uranus, civilizations could rise and fall on Earth. Time, not distance, is the true wall between us and Uranus. Space may be vast, but it is time that makes it unreachable. To cross 3 billion kilometers is not just to travel through the void, it is to travel into the future. Every mission to the outer solar system is a message sent forward in time, a conversation that will not be answered for decades. 15 years to arrive, another decade to study, 30 years to send, to wait, to learn. Even light itself, fastest thing in the universe, takes nearly 3 hours just to reach Uranus from the Sun, and another 3 hours to reflect back to Earth. Everything that happens there happens in delay. We look into the past every time we look its way. Imagine launching a probe to Uranus today. By the time it arrived, the engineers who designed it might have retired. The technologies that built it might be obsolete. The data it sent home might be interpreted by scientists not yet born. Each mission becomes a time capsule, an inheritance for the future, born of present ambition but realized only after decades of silence. That's what makes deep space exploration so haunting. It forces us to measure progress in generations, not years. The first human who dreams of touching Uranus may never live to see the attempt. The second may never see it succeed. The third may inherit a world that has moved on to other stars. Exploration beyond the gas giants is not just a question of engineering, it's a question of endurance. Our species was built to live by shorter cycles, sunrise and sunset, seasons and harvests, years and decades. The scale of Uranus stretches those instincts to their breaking point. Its orbit alone lasts 84 Earth years, longer than most human lifetimes. A single Uranian summer can outlast a civilization's age of discovery. By the time its next winter comes, languages may have changed, cultures reshaped, and memory rewritten. This is the barrier we face, not impossibility, but patience. To truly visit Uranus would mean trusting those who come after us to continue what we began, to wait for results we will never see, to interpret signals long after our voices have faded. And yet, there is beauty in that delay. Every mission we send beyond Earth is an act of faith, a reminder that discovery is not only for the discoverer. The Voyager probes, now drifting beyond the Sun's reach, still send whispers home decades after their creators are gone. They are the slow heartbeat of exploration, carrying human curiosity across time. Perhaps, then, Uranus doesn't reject us. It simply asks us to slow down, to think not in moments but in centuries, to see ourselves not as individuals chasing answers, but as a species planting questions that others will one day harvest. For now, we can only watch from afar. We can chart its seasons, map its moons, trace its storms across decades. But to visit, to stand in its faint blue light, to hear the silence of its skies, remains beyond the speed of our age. Uranus exists at the intersection of distance and time, a world forever visible yet forever postponed. It reminds us that in a universe this vast, discovery is not always about arrival. Sometimes it's about the waiting, the slow, patient unfolding of wonder that outlives us all. Uranus may be unreachable, but from its vantage, Earth is just a faint blue dot. Perhaps we are the ones being studied, not the other way around. It's easy to imagine ourselves as the observers, the curious species gazing outward, measuring, probing, learning. But out there, nearly 3 billion kilometers away, Uranus drifts in its long, silent orbit. And from that distance, we are the mystery. To any watcher on that pale horizon, if such a thing could exist, Earth would be nothing more than a dim spark near the sun, blinking faintly against the black. Through Uranus's methane haze, our world would shine only when the light was right, an invisible shimmer in the glare of daylight, vanishing for decades during the long Uranian winter. To see us, one would have to know where to look. And even then, the light that left Earth would take hours to arrive, carrying not the present, but a memory, a picture of who we were, not who we are. Perhaps that's what makes the idea so humbling. For centuries, we have treated the cosmos as a stage for human understanding, a place to project our science, our meaning, our wonder. But the universe is indifferent to our curiosity. Uranus doesn't need us to see it, it simply is, and in its stillness, in its slow, endless turning, it becomes a mirror for our own longing to know. From that vantage, Earth would seem impossibly small, fragile, glowing faintly in the inner light. All the noise of civilization, every city, every song, every moment of joy or sorrow would vanish into that single dot. To Uranus, our world would be quiet, our presence invisible. And yet, our gaze has reached it. Our machines have touched its magnetosphere, measured its storms, traced its light. In that way, perhaps the exchange is mutual. We watch Uranus, and in doing so, Uranus reminds us what it means to be observed, to be finite, to be distant, to be small. Its faint blue glow has travelled across centuries to reach our telescopes, and when we look at it, we're seeing a version of the planet that no longer exists, a frozen instant from hours ago. It watches us the same way, through delay, through distortion, through time. Science often feels like dominance, conquering the unknown with equations and data. But at its heart, it's a form of reflection. The more we study the universe, the more it reveals about ourselves. Uranus doesn't give us answers easily. It stares back with silence, with distance, with the calm persistence of something that does not need to be understood to exist. And that is perhaps its greatest lesson, that to seek meaning among the stars is also to be seen by them, that our curiosity is both a question and a mirror. Somewhere, far beyond Saturn's rings and Jupiter's storms, Uranus drifts through the dark, its methane clouds glowing with soft, cold light. And from its edge of the solar system, Earth is the unreachable one, a blue shimmer suspended in black. Maybe that's how the cosmos keeps balance. We look outward, and the universe looks back. And in that exchange, quiet, endless, and eternal, we find not dominance, but perspective. In the silence between worlds, distance becomes more than space. It becomes a reminder of our limits, and of the vastness that still awaits. When we speak of Uranus being 3 billion kilometers away, It's tempting to think of that as just a number, a vast stretch of emptiness measured in kilometers and time. But distance in the cosmos is not a line to be crossed. It's a lesson to be learned. It teaches patience, perspective, and humility. The farther we look, the smaller we become, and the more the universe reveals of itself, not through proximity, but through the beauty of separation. Between Earth and Uranus lies more than vacuum. There lies the fading heartbeat of sunlight, the cold quiet of interplanetary night, and the echoes of everything humanity has ever sent outward, our signals, our probes, our hopes stitched into radio waves. Each one stretches across that gulf at the speed of light, taking hours to arrive, carrying the faint signature of a world that refuses to be still. That space between worlds is not empty. It's full of everything that connects us. Gravity threads it. Photons traverse it. Time itself lingers within it. It's where Voyager 2 still drifts, carrying a piece of Earth farther each day, past the reach of the sun's warmth. It's where the boundary between what we know and what we imagine begins to blur. Distance, at its core, is not a barrier. It's an invitation. It's the reason curiosity exists. If the planets were close enough to touch, we might never have learned to dream of reaching them. It's the space between that drives exploration, the unknown that gives meaning to the known. When we stare at Uranus through a telescope, we are not just seeing a planet, we are seeing the measure of our own ambition. Every kilometre between here and there is a testament to how far our imagination can travel without our bodies following. Every hour of light's delay is a reminder that the universe does not hurry for us, that it moves at its own ancient pace and invites us to listen instead of rush. The silence between worlds humbles us. It asks us to confront the limits of flesh and time. It reminds us that discovery is not conquest, it's communion. That we do not own the cosmos, but share its light, briefly, as it passes by. And still, we reach. Because distance, however infinite it seems, has never stopped us. It has defined us. From the first sailors who crossed dark oceans, to the engineers who guided Voyager beyond Neptune, every journey outward has begun with the same realization. That the space between here and there is not something to fear, but something to understand. One day, we may bridge the gulf between Earth and Uranus with new engines, new generations, new patience. But even then, the meaning of distance will remain. It is the space that gives perspective, the separation that lets us see beauty clearly, the quiet that makes the music of the cosmos possible. Uranus reminds us that wonder lives not in arrival, but in the journey. That the vastness between stars is not absence, but presence, a silence deep enough to contain every dream humanity has ever dared to send into the dark. Maybe we were never meant to reach every world. Maybe some places exist only to remind us how small, fragile, and extraordinary our reach already is. Uranus drifts at the edge of what we can imagine touching, a world of distance, silence, and cold light. It is not hostile, it simply is. A planet untouched, unvisited, unclaimed, and in that untouchedness lies its purpose. It reminds us that not every mystery needs to be solved, not every horizon crossed. Some worlds exist to show us the limits of our instruments, our endurance, our need to understand. Others exist to remind us that awe itself is part of exploration. In the centuries since we first saw Uranus through a telescope, it has remained largely unchanged, its faint blue glow constant, its secrets sealed beneath clouds. We've sent machines to study it, and we've built theories to explain it, but the planet itself has never responded. It continues to orbit in its own quiet rhythm, indifferent to our curiosity. And yet, in that indifference, we find meaning. Because every time we look toward Uranus, we are reminded of what it took just to see it at all. The centuries of eyes turned upward, the generations of thinkers who refused to believe the sky ended at Saturn, the courage it takes to keep asking questions when the answers feel impossibly far away. The existence of Uranus tells us that curiosity doesn't require arrival, it requires wonder. Perhaps one day, our descendants will go there, Perhaps they'll orbit its pale horizon, study its storms, and drift through its twilight skies. But even if they never do, the lesson will remain that the act of trying, the decision to look outward instead of inward, is itself a victory. That the measure of our species isn't how many worlds we conquer, but how many we respect enough to simply watch. Uranus stands as a monument to distance, a quiet teacher at the edge of sunlight, reminding us that discovery and humility are not opposites, they are twins. Every unreachable world reflects something about the ones who reach. The farther we go, the more we see that the universe does not revolve around us. It includes us. Briefly, beautifully, impossibly. So, perhaps we don't need to go everywhere. Perhaps some places are meant to remain distant, so that we always have somewhere to point our wonder. Because without mystery, the stars would be just numbers, and the night sky would lose its voice. Uranus reminds us that not all journeys are meant to end in arrival. Some are meant to end in gratitude. Gratitude that we exist in a universe vast enough to humble us, and alive enough to invite us to dream. In the stillness of that blue world, untouched and unreachable, we are reminded of something profound. That the farther we gaze into the dark, the more clearly we see ourselves. And so, as our journey drifts to its quiet end, we return to the edge of the impossible, where Uranus still spins in silence, untouched by human hands. We've crossed oceans of distance in thought, tracing its blue storms, its diamond rains, its endless twilight. And yet, even after all our equations and dreams, one truth remains unbroken. Some places are not meant to be reached, only to be remembered. For all our science, for all our brilliance, the universe still holds corners that remind us of our limits. Uranus is one of them. Too distant for engines, too cold for machines, too patient for time itself. It waits at the border of light, a monument to everything humanity cannot yet conquer. And in that stillness lies something sacred. Because maybe it was never about reaching every world, but understanding why we can't. When we look toward Uranus, we are looking at the edge of our reach, the line between ambition and humility. It tells us that even in failure, there is beauty. Even in distance, there is connection. The light reflecting off its clouds began its journey from the sun hours ago, crossed billions of kilometers, and found its way into your eyes tonight. That light, cold, ancient, unbroken, is the closest we may ever come to touching it. And perhaps that's enough, because every unreachable world reminds us of how extraordinary it is that we've reached as far as we have. From firelight to flight, from oceans to orbit, we have already done the impossible again and again. Uranus stands not as a wall, but as a promise. That wonder still exists, waiting quietly in the dark,